This is the one short video on relations and functions. After watching this video, you will be able to understand the Cartesian product of sets, relations, the intuition behind relations, definition, the types of relations, domain and range of the relations, functions, its concept and intuition, types of functions, and domain and range of the functions. So watch this video and you will get all the stuff here. In this video, we will start a new chapter, relations and functions. So first topic is Cartesian product of sets. The Cartesian product of the sets results in a set that includes collection of all ordered pairs. I will be explaining what is meant by ordered pairs. Let's write the definition first. So let A and B be two sets. Then the set of all ordered pairs A comma B, where this element A belongs to set A and element B belongs to set B is called Cartesian product of sets A and B. It is denoted by, let me write it here. So it is denoted by A cross B. This is the Cartesian product of two sets A and B. It is a set of all ordered pairs AB such that A belongs to set A. So first element belongs to set A, first set, and B belongs to set B. We call this Cartesian product of sets. Now what is meant by ordered pair? We know that while writing coordinates, that is xy coordinates of a point in a plane, what we do, the first element x is always the abscissa and the second element is always the ordinate. That is, if I take xy plane, if I take any point, let us say this point, so let us say it is 2, 3. Okay, now this 2 means we take the x element first, and this 3 means this is y element. Okay, if I take 3, 2, okay, so let us suppose I have another point 3, 2, 3, 2. So 2, 3 and 3, 2, they are totally different. So 2, 3, this ordered pair is not equal to 3, 2, 3, 2. So this is different from this. Okay, so while writing the coordinates x, y of a point in a plane, the first element x is always the abscissa and the second element is always the ordinate. Thus 2, 3 is not equal to 3, 2. The two ordered pairs represent the distinct points in a plane. Okay, so in Cartesian product of sets, order matters. Okay, so ordered pair means that the two elements taken from each set are written in a particular order. Okay, now let's take an example. Let us suppose we have two sets here. Let us say we have two sets. We have set A, which contains elements. Let us suppose we have 1 and 3, and we have set B, which contains elements. Let us say 2, 4 and 5. Okay, then A cross B, which is, so let me write it here, A cross B is a set. Okay, so what we do, we take the first element of first set fixed and relate it with each of these elements. That is, we write first 1, okay, then we relate it with 2, then we have again 1, then we write 4, then we have again 1, then we have 5, then we take second element, which is 3, fixed and related with each element subset B, 2, likewise we have 3, 4, then we have 3, 5, 3, 5. So this is the Cartesian product of two sets A and B. Here order matters. Now we can see that A cross B is not equal to B cross A. If I write B cross A, so B cross A, so what will happen? So this time we have B is equal to 2, 4, 5 and A is equal to 1, 3. So it will be different from A cross B. So here you can see we keep this fixed and related with this. So first is 2, 1, then we have 2, 3, then we have 2, 3, then we have 4, 1, 4, 1, then we have 4, 3, 4, 3, likewise we have 5, 1 and 5, 3. Okay, so we can see that A cross B is not equal to B cross A unless A is equal to B. That means A and B are equivalent sets. Then A cross B will be equal to B cross A. By equivalent sets we mean that the two elements have same element. Sorry, two sets have same elements. That is, if A has, let us suppose 2, 3, B set B has also 2, 3. In this case, A cross B will be equal to B cross A. Now in sets we know that order did not matter. So if we have a set A which contains elements, let us say 1 and 2, we can rewrite it like this: A contains status 2, 1. So order did not matter in sets, but in the Cartesian product of sets order matters. Okay, having said that, likewise we can relate this with the Cartesian product of three sets also. That is, if I write it here, the Cartesian product of three sets, that is A, we have set A, set B and set C. The Cartesian product of set A cross B cross C is a set of all ordered pairs, let us say A, B, C, such that A belongs to set A, small b belongs to set B, and small c belongs to set C. Okay, so we can calculate that very thing also. If I take three sets, that is A is a set that contains, let us say 1, 2, B contains 3, 4, and C contains, let us say 5, 6. Then we can calculate A cross B cross C. Okay, also for this very set, for three sets. So first what will we do? We calculate A cross B. If I have the space, let me make some space. Okay, so to calculate A cross B cross C, first we calculate A cross B. Okay, so A cross B will be 1, 3, 1, 3, then we have 1 4 1 comma 4, then we have 2 3 and 2 4, so we have 2 3, then we have 2 4. So this is our A cross B. Now A cross B cross C will be equal to, since A cross B is this, so to this we cross with C. Okay, so this set we related with set C, so A cross B cross C will be equal to, so we have 1 3 5 first. Okay, so first will be 1 comma 3 comma 5, then we will have 1 3 6 1 3 6, then we have 1 4 5 1 4 5, then we have 1 4 6 1 4 6. Likewise we have 2 3 5 2 3 5, then we have 2 3 6, then we have 2 4 5 2 4 5, and then we have 2 4 6. Okay, likewise we can form the ordered pair of A cross B cross C cross N, that is if we have multiple sets here. Having said that, now there are some properties. For that, let me rub this out. First we saw that number of elements in a set, number of ordered, what we call number of elements in a Cartesian product of sets. So let us find the number of, if we have set A, it contains elements, let us suppose P, and we have set B, it contains elements, let us say Q, then the number of ordered pairs of A cross B will be equal to P times Q. That is, if set A contains 2 elements and if set B contains 3 elements, then the set of all ordered pairs of A cross B, it will be equal to 2 into 3, which is 6. Okay, so let us see, let us take two sets. So again, let us take the first example. N contains 2, B contains 3 elements. Now let us see how many ordered pairs we will get. So A cross B will be equal to, so we have 1 2 1 4 and 1 5, so we have 1 2, then we have 1 4, then we have 1 5, then we have 2, we have 3, then 3 2, then we have 3 4, and then we have 3 5. Here you can see the number of ordered pairs of A cross B will be equal to 1 2 3 4 5 6. If set A contains 2 elements, B contains 3 elements, then A cross B contains 2 into 3 6 elements, rather 6 ordered pairs. Okay, now there are other properties, that is A cross B, as I have told you, A cross B is not equal to B cross A, B cross A, unless A is equal to B, that is A and B are equivalent sets, then this will apply. Also we have the non-associative property, that is A cross B cross C is not equal to A cross B cross C. Then we distribute to our union and intersection, that is we have A cross B union C is equal to A cross B union A cross C. So you can prove them by the taking examples. Okay, our intersection, yes, they are distributive. Our intersection also, that is A cross B intersection C is equal to A cross B intersection A cross C. Our difference, they are also distributive. Our difference, that is A cross B minus C is in fact equal to A cross B minus A cross C. Okay, so if I have the time, I will be explaining them also. Let us take some questions on Cartesian product of sets. If A is a set which contains elements 1 and 2, B contains 2 and 3, and set C contains 3 and 4, determine A cross B union C, B cross A intersection C, A union B cross C, A cross B intersection A cross C. Okay, so we have the sets. So set A contains, so we have set A, it contains elements 1 comma 2. Okay, we have set B, it contains 2 comma 3, and let's take another color if I have. Okay, so let me see if I have another color. Okay, so let's take set C. C contains 3 comma 4. Okay, now since we need to find out A cross B union C, so first we need to calculate B union C. So B union C, it will be a set. So by union, what we mean, the set of all elements which are either in set B or in set C or in both. Okay, so set A is this, set B is this, set C is this. So we have 2, 3 and 4. Then A cross B union C will be equal to, so we have this A cross B union C. So what will be the elements here? So the elements will be, so we write first 1, 2, so we have 1 comma 2, then we have 1 comma 3, then we have 1 comma 4, 1 comma 4, then we have 2, 2, so we have 2 comma 2, then we have 2 comma 3, then we have 2 comma 4. This is our A cross B union C. Likewise, we can calculate B cross A intersection C. So first we need to find out A intersection C. It will be a set. So intersection shows only the common elements in two sets. Since we have A and C, what are the common elements here? In A and C, there is no common element here. So A intersection C is phi here. Okay, let us write it here. So it is phi. Therefore, B cross A intersection C, it will be also empty. That is, if one or both sets are empty, then A cross B is empty. In this case, we have two sets here. Okay, if one is empty, then A cross, the Cartesian product of one set and another empty set, it is also an empty set. Okay, now we can also calculate A union B cross C. You can calculate it by yourself. So A union B, if I write it here, we have A union B. Let's find out the A union B first. So we have A and B So what are union means the set of all elements which are in set A, in set B, or in both. So we have 1, 2 and 3. This is our A union B. Since we need to calculate A union B cross C, A union B cross C, it will be equal to, or let's write it here, A union B cross C, it will be equal to, since C is 3 and 4, so we relate, so we have 1, 3, 1, 3, then we have 1, then we have 2, 3, 2, 3, then we have 2, 4, we have, I have done the mistake, so we have 1, 3, then we have 1, 4, then we have 2, 3, 2, 3, then we have 2, 4, 2, 4, then we have 3, 3, we have 3, 3, and then we have 3, 4. Okay, now you can also calculate then A cross B intersection A cross C. You can calculate it by yourself. So what are relations in mathematics? Before defining them, let's take a simple example. Let us say we have a set A which contains famous supports persons, set B contains the supports. Let's take the Cartesian product of these two sets, A cross B. Okay, so A cross B is the Cartesian product of these two sets, A and B. By Cartesian product, what we mean, Cartesian product of sets results in a set that includes collection of all ordered pairs. Ordered pair means that two elements taken from each set are written in a particular order. Here the order is, we write, to form an ordered pair, we write first element of set A and then first element of set B and form one ordered pair. Then we take first element of set A and then we take second element of set B and form another ordered pair. Okay, so here what will be the ordered pair? So first we have Ronaldo, football, it will be one ordered pair. Then we take Ronaldo, tennis, second ordered pair. Then Serena Williams, football, here. Then we have Serena Williams, tennis. Then we have Tiger Woods, football, here. Then Tiger Woods and tennis. So these are the Cartesian product of set A and B in this example. Now let's define the relationship here. Okay, so to define the relationship, let us write the definition. A relation is a connection or rule between elements of two or more sets. Two or more sets defined as a subset of the Cartesian product of those sets. By this what we mean, let me explain. So let us take a relation here. So what will be a relation? A relation is a connection between elements of two or more sets defined as a subset of the Cartesian product of the sets. A relation is also a set here. Okay, so let me define here. Let us define a relation here. So our relation will be a set of ordered pairs A comma B such that A plays B and A belongs to set A and B belongs to set B. Okay, what is a relation? A relation is a connection between the elements, and in this case what will be our relation? We have defined the relation plays. Okay, in this example our relation will be also a set of ordered pairs which are connected, where there is connection between two elements of two sets. Okay, so since we have the famous supports persons and we have the supports here, now here we need to find out what is the relation. Ronaldo plays football. Okay, this will be in a relation because A plays B, so we have defined it A plays B. So Ronaldo is related to football. Serena Williams is related to tennis. Okay, so in the relation we have also a set of ordered pairs. So here we will have a set of ordered pairs. We have Ronaldo football, and Serena Williams tennis. Okay, here you can see a relation is a connection between the elements of two or more sets. So Ronaldo is related to football, Serena Williams is related to tennis. So it is actually a subset of the Cartesian product of those sets. So here you can see this R is in fact the subset of this Cartesian product of two sets A and B. Okay, now relations can be if I define it using the proper, so here we can see relation is in fact a subset of A cross B, Cartesian product of sets. Let us take another example. Let us say we have set A which contains element 3 and 4 and set B contains elements 1, 2 and 5. The Cartesian product of these two sets A cross B will be, so Cartesian product is also a set of all ordered pairs. Okay, so 3, 1, so this is one ordered pair, then we have 3, 2 here, then 3, 5, then we have 4, 1, 4, 2 and 4, 5. This is the Cartesian product. Now let us define the relation here. So let us define the relation. So let us write our relation is a set that contains ordered pairs A and B such that A is greater than B and A belongs to set A, B belongs to set, or let me put it like this, B belongs to set B. Okay, so the relation we have defined here is greater than. Okay, then in our relation will be a set. So since we have defined that A is greater than B, here we can see 3 is greater than 1. So first ordered pair will be 3, 1. So I will not use the color combination here. So 3, 1, that will be in the relation. Then 3, 2, 3 is greater than 2, that will be also in relation. 3, 2, 3, 5, 3 is less than 5, so it will not be in the set of relations. 4, 1, yes, it will be 4, 1. Then we have 4, 2, 4 is greater than 2, 4 is greater than 2. 4, 5, 4 is less than 5, so it will not be in the set of relations here. Okay, so this is the relation we have defined here. Also we can define, in this case, if we have these two sets, and here you can see a relation is a subset of the Cartesian product of sets. Here you can see R is the subset of A cross B. Okay, now how do we write the relations? If we want to write the relations here, if ordered pair AB belongs to a relation R, then we say, or we write A or B, that is A is related to B, okay. If ordered pair AB does not belong to relation, we say, or we write it like this: A is not in relation to B. Okay, now we can also define the domain of the relation R. So the domain of the relation R from set A to set B, if I have the space, let us define the domain here also. Domain of relation. Okay, so, and let me create some space. Domain of relation or from a set A to set B is the set of all first elements of the ordered pairs which belong to a relation. So we can write domain of R, domain of a relation R is a set that contains the first element A such that A belongs to set A and ordered pair AB belongs to a relation. Simply, in this case, what will be the domain? So domain in this example will be the set of all first elements of ordered pairs which belong to set or which belong to the relation or here. So what are the first elements here? We have 3, 3, 4, 4. So repetition, we don't take the repeated what we call the elements. We write only ones. So we have 3, 4. So this is the domain. Now let's define the range. So range of relation or is the set of all second elements of the ordered pairs which belong to R, that is relation. That is, if I write range will be range, or let's write it here, range of R will be, in this case, what will be the range, or let's write it in the set builder form first. So range will be a set of second element which is B, such that B belongs to set B and AB belongs to relation. So what is meant by this? In the given question, so we got this as the relation. Okay, so range for this question will be the set of all second elements of ordered pair. Okay, so second elements of the ordered pairs. So what are the second elements? We have here 1, here we have 2, 1 and 2. Again we write without repetition 1 comma 2. That will be the range for this question. So domain is 3 and 4 and range is 1 comma 2 here. Now let's learn about domain and range of a relation with an example. Let R be a relation from set A, which contains 2, 4, 5 as elements, to set B, which contains 1, 2, 3, 4, 6, 8. Defined by the relation A is related to B, which implies A divides B. Here the relation is A divides B. Write R as a set of ordered pairs. That is, we need to form a set of relations here. We need to form the relation as a set of ordered pairs. We need to find out domain and range of R. Okay, before defining domain and range, let us first find out the relation here. Okay, so relation will be the set of ordered pairs. Our relation here is, we have set A which contains, so we have set A which contains elements 2, 4, 5, and we have set B which contains 1, 2, 3, 4, 6, 8, and our relation is defined here, that is A divides B. We have a set of ordered pair like this, that means A divides B. So A is the element of first set and B, A's are the elements of first set and B's are the elements of second set. Now let us see what will be in our relation. And we know that if we want to find out the number of ordered pairs of Cartesian product here, so the number of ordered pairs in the A cross B, it will be equal to 1, 2, 3, that is 3 into 1, 2, 3, 4, 5, 6. So we will get 18 ordered pairs. We will get the Cartesian product of sets will be 18 ordered pairs. Okay, but we are not concerned with 18 ordered pairs here. We only need to find out those ordered pairs which satisfy this condition, that is A divides B. Okay, in the Cartesian product of two sets here, the total number of ordered pairs will be formed 18. That is the number of elements in set A, which is 3, times the number of elements in set B, which is 6. So we will get 18 ordered pairs. But we are not concerned with that. We only need to find out what set will we get as the relation. Okay, our this condition should be satisfied. A divides B. So these are A's, these are B's. Let us see. Does 2 divide 1? No. Does 2 divide 2? Yes. So first order pair will be 2, 2. Then does 2 divide 3? No. 2 divides 4? Yes. So second will be 2, 4. 2 divides 6? Yes. We have 2, 6. 2 divides 8? Yes. 2, 8. Now 4 divides 2? 4 divides 1? No. 4 divides 2? No. 4 divides 4? Yes. So we have 4, 4. Does 4 divide 6? No. 4 divides 8? Yes. So we will have 4 and 8. So this will be R as a set of ordered pairs. Okay, so we will have 1, 2, 3, 4, 5, 6. as which satisfies this relation A is related to B such that A divides B. But in the Cartesian product of these two sets, we will get 18 ordered pairs. But we are not concerned with those 18 ordered pairs. We are only concerned with those ordered pairs which satisfy this relation, that is A divides B. These are only 6 here. Now let's come to the domain. What is meant by domain? Domain of a relation R from set A to set B is the set of all first elements of ordered pairs which belong to R. That is, domain of R is the set of all first elements such that A belongs to set A and ordered pair AB belongs to the relation. Now here domain of R will be, these will be the domain. The first element is the set of all first elements of ordered pairs of the relation. So domain of R will be, domain of R will be, so we have 2, so we don't take the repetitions here, so we have 2 comma, here we have 4. So this will be the domain of this relation. I will be explaining it with an arrow diagram also, so bear with me. Now what is a range? Range of relation R is from set A to set B. From set A to set B is the set of all second elements of ordered pairs which belong to R. Okay, range of R is set of all the second elements B such that B belongs to set B and AB belongs to R. So here the second elements of a relation set of ordered pairs of relation form the range. So we have range of R will be the second. So we have here 2, 4, 6, 8, 4, 8. So we don't take repetition. So we have 2, 4, 6 and 8. That will be the range of relation R. Now if I want to explain these things using arrow diagram, I will be explaining that very thing also. But here one more thing is, what is meant by codomain? Codomain is simply the elements of second set. Okay, whole second set. In this case codomain will be 1, 2, 3, 4, 6 and 8. Okay, now let us define it another way. For that, let me rub this out. Okay, we have this question and we will be defining it using the arrow diagram. So we have two sets here. Set A, okay, I am out of bound. So we have set A which contains elements, we have 2, 4, 5, 2, 4, 5. Okay, then we have set B which contains elements. So in set B we have 1, 2, 3, 4, 6, 8. 1, 2, 3, 4, 6, and 8. Okay, now in the relation what we got, the relation was A divides B, and we got this relation 2, 2, 2, 4, 2, 6, 2, 8, 4, 4, 4, 8. That is, we got this very relation here. That is 2 divides 2, 2 divides 4, 2 divides 6, and 2 divides 8. Okay, this was 1. These are the set of ordered pairs. Also we got 4 divided 8, 4 divided 4, and 4 divided 8. Now, how do we define the domain? Now, domain means all those elements of first set which have an image in the second set. Okay? All those elements of first set which have an image in the second set is called the domain. Now, here you can see 2 has an image in the second set as 2. 2 has an image as 4. The image of 2 is 6. The image of 2 is 8. So we say 2 has the images here. So we call 2 as in the set of domain. Likewise, 4 has an image in second set. 4 has image in the second set. So these are in the domain. What about 5? 5 has no image in the second set, so 5 will be not the part of the domain. So domain, all those, let me write it here, all those elements of first set which have an image in second set. Okay, they will be the domain of the relation. So here domain is since 2 has the image in the second set, 4 has the image in the second set, so we say domain of this relation is 2, 4. What about range? So we say all those elements of second set which have a pre-image in the first set. Okay, all those elements of second set which has a pre-image in the first set. Here you can see B is in the second set, but 1 is in the second set, but it has no pre-image in the first set, so 1 will not belong to range. 2 has a pre-image in the first set as 2. 4 has a pre-image in set A as 2. 6 has a pre-image in the first set as 2. 8 has a pre-image in the first set as 4. Okay, and 4 is also another pre-image as 4 in the first set. Okay, so we say all those elements of second set which have a pre-image in first set. Okay, so range will be so we have 2, 4, 6 and 8, because 2 has pre-image, 3 has no pre-image, 4 has pre-image, 6 has pre-image, 8 has pre-image. So in the range we will have 2, 4, 6 and 8. This will be our range. Now what about codomain? As I have told you, codomain is simply whole second set. All the elements in the second set are codomain. Okay, so codomain, all elements elements of second set. Whether they have pre-image or not will be classified as codomain. So codomain will be codomain in this case will be the whole set B, that is 1, 2, 3, 4, 6 and 8. Okay. Now let us define identity relation in a set. The identity relation in a set A is the set of all ordered pairs A comma B belongs to the Cartesian product of A with itself, that is A cross A, such that A is equal to B. That is to say, the set of all ordered pairs that belong to A cross A for all A belongs to set A. It is denoted by I subscript A. Okay, so in set builder form we can write that is the identity relation on a set with itself is the set of all ordered pairs A comma A such that A belongs to set A, B belongs to set A and A is equal to B. Now how do we define? Let us define it with an example. Let us suppose we have a set A which consists of elements. Let us suppose 1, 2, 3 and 4. Okay, then the identity relation, that is I subscript A, the relation of a set with itself, it will be equal to, since we have all the ordered pairs where A is equal, that is A is equal to B. If A and B are two elements that belong to A cross A, the relation is that A should be equal to B. Okay, that will define our relation. Now the relation of a set with itself will be the set of all ordered pairs where A is equal to B. So here the set of ordered pairs will be, that is first 1 is related with 1, okay, because A is equal to B, that is A is equal, if I define it with this set builder form, so the set of all ordered pairs A comma A, that is 1 comma 1, such that A belongs to set A, 1 belongs to set A, B, which is also 1 here, belongs to set A here, and A is equal to B. Then next we will have 2 comma 2, then we have 3 comma 3, and then we have 4 comma 4. That will be the identity relation in a set with itself. Okay, so we can write it like this also. So in A cross A we will have, here we have 1, 2, 3, 4, 16 ordered pairs. Out of those ordered pairs in A cross A, only the relation of a set with itself, it will consist of 1, 2, 3 and 4 ordered pairs only. Because if I write here A is equal to again 1, 2, 3, 4, then our A cross A would have been, so in A cross A we would have, here we have 4 elements, here we have 4 elements, so we will have 16 ordered pairs, 4 into 4. Out of those 16 ordered pairs, the identity relation in a set will have only these ordered pairs where A is equal to B. Okay, this is the identity relation in a set. Now next let us define the inverse of what we call inverse of a relation. Now let us define the inverse relation. Inverse relation. Now let us suppose let R be a relation from set A to set B. The inverse relation of R, it is denoted by R superscript -1. Okay, so R inverse, it is denoted by this is a relation from B to A, and it is defined by that is R inverse will be the set of all ordered pairs, that is B comma A, such that AB belongs to the relation R. That is R inverse consists of those ordered pairs which, when reversed, belongs to R. Now here obviously the domain of R inverse is the range of R, and range of R inverse will be domain of R, and let me write it here. So domain, I will explain it with an example. Domain of R inverse is equal to range of R, and range of R inverse will be domain of R. Now let's take an example. Let us suppose we have a set. Let A is a set consists of elements 1, 2, 4. Let us suppose, and let us take another set B, which contains elements 2, 3, and 5. Now, and let us define here a relation. That is, let us define, how do we define or B, the relation. So we take a relation here is less than from A to B, then so what is our relation here? So let us write the relation first. Will consist of all ordered pairs so let us suppose the relation is the set of all ordered pairs AB such that A belongs to A and B belongs to set B, and A is less than B. So this is our relation in set builder form. Now let us write it, and let me so our relation will be the set of all ordered pairs. So we are first defining R, then we will take the R inverse. So in R, what will be our ordered pairs? So relation is less than. Okay, so we have 1, 2, 1 is less than 2, so it will be in our relation set. So we have 1, 2, then is 1 less than 3? Yes. Then we have 1, 3, 1 is less than 5? Yes. 1, 5. Then we take 2 is equal to 2, so that will not be the part of relation. Is 2 less than 3? Yes. So we have 2, 3. Then 2 less than 5? Yes. So we have 2, 5. Then 2, then we have 4 is greater than 2, 4 is greater than 3, but 4 is less than 5. So we have 4, 5. This will be the relation, the set of all ordered pairs where A is less than B. Okay. Now R inverse is simply when we reverse the order here, we will get. So in R inverse, what will we have? We will have B comma A such that, or let me write it here, such that A comma B belongs to R. Okay. So in R inverse, we will have these elements but in reverse order. So we'll have 2 1 3 1 5 1, then we have 3 2, then we have 5 2, then we have 5 4. This will be the relation, that is the inverse relation. So first we take the relation, then it is inverse, we reciprocate, we reverse the order of the ordered pairs. Okay, now let us learn the key differences between a reflexive relation and identity relation. A relation R in a set A is said to be reflexive if A is related to A for all A belongs to set A, that is, the ordered pair A comma A belongs to the relation for all A belongs to set A. That is, every element in a set relates to itself but might relate to others too. That is the reflexive relation, and I will be explaining with an example. What is identity relation? A relation in a set A is the set of all ordered pairs, that is, the set of all ordered pairs belongs to A cross A such that A is equal to B. In set builder form we can write the set of all ordered pairs A comma B such that A belongs to set A, B also belongs to set A, and A is equal to B. Okay, now let me show what is the difference. So let us take a set. Let us suppose we have set A where we have the elements 1 comma 2 comma 3. Okay, now let's take the reflexive relation. So let us take the reflexive relation here. Now every element in set A relates to itself but might relate to others too. Let us take the relation, that is 1 is related to itself, that is 1 comma 1. We will have 2 comma 2, 2 comma 2, then 3 comma 3. Then possibly we can take 1 comma 2, 1 comma 2 also. We can take 1 comma 3 also, 1 comma 3, and so on. This will be the reflexive relation because every element in set A relates to itself. Okay, so 1 is related to 1, 2 is related to 2, 2, then we have 3, 3. Then potentially we can have 1 is related to 2, 1 is related to 3. That will be the reflexive relation. But what is the difference here? What is the idea behind this? That is, every element must be paired with itself, but other pairings are also allowed. Okay, but identity relation, in identity relation, what we take, so how do I write it? So let me denote it by this. In identity relation, every element must be paired with itself only. Okay, so let me write it here. If I have the space, or let me form the pair. So we have 1 comma 1, 2 comma 2, then we have 3 comma 3. This is the identity relation. Identity relation, and this is the reflexive relation. So the key difference is, in a reflexive relation, every element must be paired with itself, but other pairings are also allowed. If we have this set, so 1 1 2 2 3 3, these are to be taken, but we can take 1 2 1 3, or we can take 2 3 also here. Okay, so this is the reflexive. But in case of identity relation, every element must be paired with itself only. Okay, so 1 is related to 1, 2 is related to 2, 3 is related to 3. We cannot take other relations here, only those ordered pairs where they are related with each other. Okay, so if I write it here, so identity, in case of identity relation, what we take the self relations. Okay, self only, like this 1 1 2 2 3 3. But in case of reflexive relation, we take self, that is 1 1 2 2 3 3, plus we can take potentially others. Here we can see identity relation is always a subset of reflexive. Okay, so identity relation is the subset of reflexive relation. Now let us discuss about the symmetric relations. A relation R in a set A is said to be symmetric if the ordered pair AB belongs to R and A is related to B, implies B is related to A. That is, if the ordered pair AB belongs to R, it implies the ordered pair B comma A also belongs to the relation R. Thus, a relation R in a set A is said to be symmetric if and only if R is equal to inverse of R. That is, if R is the relation, then if it is inverse is also equal to the relation, then we say the given relation is symmetric. Now, for example, let A be the set of all triangles in a plane. The relation R in the set A defined by, so we take this relation, that is symmetric since AB belongs to set A, which is the set of all triangles. Then A is similar to B, triangle A is similar to triangle B, let us suppose, which implies triangle B is also similar to triangle A. That is, if A is related to B, implies B is related to A. That is, if I take, let us say, A is a set of all triangles in a plane. Let me take two triangles here. Let us suppose we have triangle this A and we have this triangle B. Okay, now what happens here, if I define, so the relation will be symmetric here since our relation is similar to, so we will have the triangle A is similar to itself, so we get AA. Then A is similar to B. Okay, then we have B is similar to B and B is similar to A. So this set, if I take these two triangles in a plane, then this relation, that is, triangle A is similar to itself, triangle A is similar to triangle B also, triangle B is similar to itself, and triangle B is similar to A also. So this will be our symmetric relation. And let me take the help of numbers to explain it more. So let us take a set. Let us suppose we have A is a set containing elements, let us suppose 1, 2, 3 and 4. Okay, if I take the relation R like this, so if I take 1 comma 2, okay, then if I take 2 comma 1, then we have 3 comma 4 and we have 4 comma 3, then we have 4 comma 4. We say this relation is symmetric. Why? Because we have told if A is related to B, then B is also related to A. Here, if I take its inverse, let us take the inverse also to explain. So the inverse, simply we swap the ordered pairs, the elements in the ordered pairs. So if we have 1, 2, we write 2, 1. Here we have 1, 2. We have here 4, 3. Here we have 3, 4 and 4, 4. Okay, here you can see all the elements in R, all the ordered pairs in relation R are also in this R inverse. Okay, so order does not matter in a set because R inverse is a set. So this is one element and this is 2 element. If I write 2, 1, if I write 1, 2 here, this ordered pair here and this, so order does not matter in sets, but in but ordered pairs, the elements in the ordered pairs matter. Here we can see if this is A, this is B, if this is A, B, A, B, A, B, this is only for the sake of understanding. Here A is 1, B is 2. Now here we have A is 2, B is 1. Clearly AB is equal to BA, which we have written here. If this set AB is belongs to the relation, then BA also belongs to the relation, and this is true for all the ordered pairs here. Okay, now let us take the example where we don't have the symmetric relation from this. So if I take the ordered pair, let us say 1, 2, 2, 1. I also take 3, 4, and I take 4, 4. Clearly this is not the symmetric relation. Why? Here 1, 2, or here 2, 1 is also here, that is A is related to B and B is related to A. Also here you can see 3, 4 is here, but its counterpart 4, 3 is not present here, so that will not be a symmetric relation. So if I take its inverse here, you can see, so we have 2, 1, here we have 1, 2, here we have 4, 3, here we have 4, 4. Here we can see 3, 4. Okay, so 3, 4 belongs to R, but 3, 4 is not present here. That is 3, 4 is not in the inverse of this relation A. Okay, so let's take another relation R1. Let us suppose it consists of 2, 2, then we have 3, 3, then we have 4, 4. Okay, here we can say if A is this, if I take this relation, so 2, 2, 3, 3 and 4, 4, this is symmetric. Why? If I take it as inverse, that is R inverse, we will get again 2, 2. So swapping the same elements in ordered pairs doesn't change anything. So we have 2, 2, then we have 3, 3, and then we have 4, 4. So this is symmetric. Why? Because R is equal to R inverse here. Now let us discuss about transitive relations. A relation R in a set A is said to be transitive if A is related to B and B is related to C, which implies A is in, that is, it must be the case that A is related to C. That is, if the ordered pair AB belongs to the relation R and ordered pair BC belongs to the relation R, that it must be that the ordered pair AC must belong to the relation R. The example is, let L be the set of all lines in a plane and R be the relation in or be the relation in set L defined by is parallel to. Then if we have A, B and C which are in set L, which belong to set L, such that A is parallel to B. If A is parallel to B and B is parallel to C, then it must be A is parallel to C. That means R is transitive. So if I write it like this, so if we have A, B and C, we have three lines here. Okay, there can be infinite number of times lines here. Let's take the three cases here. Now if I define the relation, that is parallel to parallel to, so in this case the relation, that is, if A is parallel to B, then we have this ordered pair, and when B is parallel to C, here B is parallel to C, then it must be A is parallel to C. So this set R is said to be transitive here. When we say A is equal to B and B is equal to C, it must imply that A is equal to C. That is the essence of this transitive relations. Now let us take another example. Let us suppose we have a set containing numbers 1, 2 and 3, and let's define the relation. Let us define the relation is less than. Okay, in this case, so then R will be the set of all ordered pairs which satisfy this relation. That is, if I take 1 is less than 2, 2 is less than 3, then it must be that 1 is less than 3. That ordered pair should also be here. So 1 is less than 3. Then we say that this relation R is transitive. Okay. Now let us discuss about the equivalence relations. So far we have talked about the reflexive relations, symmetric relations and transitive relations. A relation R in a set A is said to be an equivalence relation if R is reflexive, symmetric and transitive. That is to say, if these three properties are followed by a relation, then we say the given relation is equivalence. That is, the first property is R is said to be reflexive if A is related with itself or potentially with others. That is, A is related to A. For all A belongs to set A, we say R is reflexive. If A is related to B, it must be that B should also be related to A. For all A and B belong to A, we say R is symmetric. And third property is, if A is related to B and B is related to C, then it must be that A is related to C. For all A, B, C belong to set A, we say R is transitive. If any one of these properties is absent, we say the given relation is not the equivalence relation. We have taken here example. Let A be a set of all triangles in a plane, and let R be the relation in set A defined by, so we have defined this relation is congruent to. Then A is related to A for every A belongs to A. Why? If we have, let us say we have A contains, or let us define it, so A contains triangles which are congruent. That means they have equal angles and equal sides. So we have, let us suppose, this is only for the sake of understanding, it has nothing to do with we don't write them in this fashion. So let us say this is A triangle, this is B triangle, this is C triangle. Now when I say A is related to A, that is A triangle is congruent with itself. Since every triangle is congruent to itself, we say R is reflexive. Okay, so this property is satisfied. Also, if A is related to B and relation is congruent to, and then it must be that B is related to A. Here we can see, since A triangle is congruent to B triangle, then it implies that B triangle is also congruent to A triangle. So that is what I have written here. Since if a triangle A is congruent to another triangle B, then triangle B is also congruent to A. That means R is symmetric. That is the second property. Now third is, if triangle A is related to triangle B and relation is here congruent. If triangle A is congruent to triangle B and triangle B is congruent to triangle C, then it must be that triangle A is congruent to triangle C. That is, A is related to C. Then we say R is transitive. That is, if triangle A is congruent to triangle B and we have B triangle is congruent to triangle C, then it must be that triangle A is congruent to triangle C. Then we say R is transitive. Okay, so this is how do we define what we call the equivalence relations. We can take another what we can example. Let us suppose, let L denote the set of all lines in a plane, and let us denote the relation R, that is on a set L. Let us define the relation is parallel to. Okay, and let us suppose we say then R is equivalence relation. Okay, if A is parallel to A for all A belongs to set L, we say R is reflexive. We know that if we have three lines, parallel lines, if this is A, B and C, if A is, we know that a line is parallel to itself, that is, A is related to A for all A belongs to L, we say R is what we call reflexive. Likewise, if line A is parallel to line B, it must be that line B should also be parallel to line A for all A, B belong to L. So we say R is symmetric. Likewise, if A is parallel to B and B is parallel to C, it must be then A should be parallel to C for all A, B and C belong to set of lines L. That is, if A is parallel to B, B is parallel to C, it implies A is parallel to C. Then we say this R is transitive also. If all reflexive, symmetric and transitive properties are satisfied, we say the relation is equivalence, or we say we have the equivalence relation. Let us take some examples on relations. Let A be a set containing elements 1, 2 and 3 and B be the set containing elements 2, 3 and 4. Which of the following are relations from A to B, that is A cross B? We have two here, two sets given here. So first thing is, let us first find out A cross B, that is Cartesian product of A and B. So A cross B will be the set of all possible ordered pairs which we can make from these, such that first element of the ordered pair is from set A and second element of an ordered pair is from set B. So we have A. In A we have 1, 2 and 3, and in B set we have 2, 3 and 4. To form the Cartesian product, what we take, we form this ordered pair first. So we have 1, 2, then we have 1 3, then we have 1 4, then we take 2 2, then we have 2 2, then we have 2 3, 2 3, then we have 2 4, okay, then we have 3 2, 3 3 and 3 4. So we have 3 2, 3 3 and 3 4. So this is the Cartesian product of the two sets A and B. The question tells us which of the following are relations from A to B. So let us see. We have here we have relation 1 3. If all the elements of this set are present in this A cross B product, then we say this set is in relation to the Cartesian product of A and B. Here we have 1 3, here we have also 1 3, 2 2, let us see, 2 2 is here also, 3 4, 3 4 is also here, and we have 1 4, 1 4 is also here. Therefore we can say, let us say this, let us denote it by R1. Okay, I will not write all this stuff. That means this relation first is the subset of A cross B. We know that relation between two elements A and B is always a subset of the Cartesian product of these two elements A and B. Since every element in this set are also present in the Cartesian product of A and B, we say what we call this first one is a relation from A to B. Okay, and this in fact is the relation. Now let's take the second one. In the second one we have 1 2 1 2 here. Okay, no problem. Here we have 2 1, but 2 1 is not present in the Cartesian product of this A and B. Okay, so we can say this, that is, let me write it, 1 2, 2 comma 1, 2 comma 3 and 2 comma 4. How do I show it? Okay, so let us use this very simple, is not a subset of A cross B. Then we say that this set is not in relation from A to B or A cross B, but the first one is in relation to A cross B. Which of the following ordered pairs belong to the given relation? So relation is a set of all ordered pairs x, y such that y is equal to 1 minus the absolute value of x, and we have been given the ordered pairs. These we need to find which of these ordered pairs belong to this relation. This is the first question. Okay, now here the first entry of the ordered pair is denoted by x. These are x's, and the second entry is denoted by y. That is to say, let me write it here, for ordered pair this first ordered pair 1 comma 0, it implies x is 1 and y is 0. Okay, therefore the relation is this, y is equal to 1 minus the absolute value of x. Okay, so since y is equal to 0, let us write it here, 0 is equal to 1 minus, what is x? X is 1 here, so the absolute value of 1 is 1 itself. So here we will get 1 minus 1, which is equal to 0. Since 0 is equal to 0, we say this ordered pair belongs to this relation. Now let's take second ordered pair. Okay, so for ordered pair, this negative 2, negative 1, negative 2, negative 1. Here x is negative 2, y is negative 1. Relation is this. Now let us see, since y is negative 1, negative 1 should be equal to 1 minus x is negative 2. So we have here negative 2, that is the mod of negative 2. We know that the mod of negative 2 is positive 2, so it will become 1 minus 2, which is equal to negative 1. Since negative 1 is equal to negative 1, so we say this ordered pair also belong to this relation. Okay, now let us take the third ordered pair. We have for ordered pair we have 7 comma negative 6. I don't need to write what is x and y, you know it. So relation is y is equal to 1 minus absolute value of x. So y is negative 6 should be equal to 1 minus the absolute value of 7. So which is equal to 1 minus 7, which is equal to negative 6. That is, this is equal to this. That means this ordered pair also belongs to this relation. Now let us take the last one. So we have negative 3 and 4. So this is x, this is y, and relation is this: y is equal to 1 minus the absolute value of x. Now here y is 4, 1 minus the mod of negative 3, which is equal to 1 minus 2, which is equal to negative 1 here, and which is not equal to 4 here. That means this ordered pair does not belong to the relation, the given relation. Okay, this was first question. Now for second question we can also do the same. So let's take the first. So we have the set of ordered pairs x y such that x y is equal to 12. So for ordered pair, let's take the first ordered pair 3 comma 4. Relation is x times y should be equal to 12. So x is 3, y is 4. So we have 3 into 4, which is equal to 12. So here we have 4, 3 4s are 12. So this is in fact the part of this belongs to the relation. Let's take the second one. So likewise we have the second one, we have 4 3. So since x y is equal to 12, that means 4 3, 4 into 3, which is also equal to 12. That means this belongs to this relation. Now let's take 12 into 0. So 12 into 0 is equal to 0, which is not equal to 12. So this is not the part of ordered pair. Likewise 0 into 12, if I take x into y is equal to 12, so 0 into 12 is equal to 0, which is not equal to 12. So this also does not belong to this relation, this ordered pair. Let's take last one. So we have x into y minus 12. So this is x, this is y. 12 into 1, which is equal to 12, which in fact is equal to 12. So this is the part of, this belongs to the ordered pair. This ordered pair belongs to this relation. Question is, determine the domain and range of the following relation. That is, R is a set of all ordered pairs x comma 1 upon x such that x lies between 0 and 6 and x is a natural number, or x belongs to the set of natural numbers. Now let's rewrite it. So we can write it like this. This relation, that is, we have this, the set of ordered pairs x comma 1 upon x such that x, so x lies between 0 and 1 exclusively. So we have x is 1, 2, 3, 4 and 5. Okay, now our relation will be, so R will consist of, so if x is equal to 1, then 1 upon x will be also 1. So we have, if I write it like this, so first we have 1 comma 1 upon 1, this is one ordered pair. Then we have, if x is equal to 2, so we have 2 comma 1 upon 2. Likewise, x is 3, when x is equal to 3, we have the ordered pair 3 comma 1 upon 3. Then we have 4 comma 1 upon 4, and then we have 5 comma 1 upon 5. Okay, now what is the domain? Domain of R, that is the set of first entries of this relation R, will be our domain. So domain will be the set of first entries of this relation. So we have 1, 2, 3 and 4, 1, 2, 3, 4 and 5, 1, 2, 3, 4 and 5. This will be the domain. And what about range? Range of relation R will be the set of second entries of this relation. So range will be the second element. Okay, so we have 1 upon 1 is 1, then 1 upon 2, 1 upon 3, 1 upon 4, 1 upon 5. This is the range here. Let us take a question on the reflexive, symmetric and transitive relations. Give an example of relation which is reflexive but neither symmetric nor transitive. Second question is symmetric but neither reflexive nor transitive. Then third question is transitive but neither reflexive nor symmetric. Then fourth is reflexive, symmetric and transitive. And last one is neither reflexive nor symmetric nor transitive. Okay, so for that what we have done, we have taken a set which contains the elements 1, 2, 3, 4. And then we take the Cartesian product of the set with itself, that is A cross A. It will contain these very ordered pairs here. That is, since we have 1, 2, 3, 4 elements, then A cross A will be 4 into 4. That will, we will have 16 elements. Here we can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 and 16. That is, if A contains 4 elements, A again contains 4 elements, then A cross A, which will be the Cartesian product of set A with itself, it will be, there will be 16 ordered pairs. That is 4 into 4, which is 16 ordered pairs, which we got here. And we also know how to form the ordered pairs. Okay, so if A contains 1, 2, 3, 4, again A contains 1, 2, 3, 4. First A is, we form this with 1 to 1, then 1 to 2, 1, 3, 1, 4. So first we will have 4, then that is 1, 1, 1, 2, 1, 3, 1, 4. Then we take 2, so we have 2, 1, 2, 2, 2, 3 and 2, 4. Sorry, 2, 4. Likewise, then we take 3, then we have 3, 1, 3, 2, 3, 3 and 3, 4. So we have 3, 1, 3, 2, 3, 3 and 3, 4. Then lastly 4, 1, 4, 2, 4, 3, 4, 4. So we will get 16 ordered pairs. Now we have to give an example of the relation which is reflexive but neither symmetric nor transitive. So first we need to learn what is meant by reflexive relation, symmetric relation and transitive relation. Okay, I have explained it earlier. So Let me explain it again. So a relation or on a set A is said to be reflexive. Okay, that is, if A is in relation to A for all A belongs to set A, we say the relation is reflexive. That is, in simple terms, elements or every element must be paired with itself, but other pairings are also allowed. So first thing is, every element must be paired with itself, but other pairings are also allowed in case of reflexive relation. Then we have symmetric relation, in which we say a relation is symmetric if, that is, if we have A is related to B, which there must be, that is the case, B should also be related to A for all AB belong to set A. Now here what happens, every element must be paired with itself only, other pairs are not allowed, sorry. Okay, then we have the transitive relations. So if A is related to B and B is related to C, then this must be the case that A should also be in a relation to C for all A, B, C belong to A. Okay, now keeping this in mind, let us form the relations. So first relation that we can form, so let us take the relation R1, and I will explain. So in R1, if I take element is 1, 1, 1, 2, and let us take 2, 2 also, 2, 3, 3, 3, and 4, 4. Now this relation is reflexive. Why? Because for all A belongs to set A, this ordered pair AA also belongs to relation R1 here. That means R1 is reflexive. So what I have told you, what is meant by reflexive relation, every element must be paired with itself. So 1 is paired with 1, 2 is paired with 2, okay, 3 is paired with 3, 4 is paired with 4, okay. But other pairings are also allowed. That is, 1 is paired with 2, we can also take this. 2 is paired with 3, so these can be also taken in case of reflexive relations. Now this is reflexive relation. Now we have to show that it is neither symmetric nor transitive. So here we can see 1, 2, this 1, 2, it belongs to R1, okay, but 2, 1 is missing here. 2, 1 does not belong to R1. Okay, for symmetric, 1, 2 is here, but 2, 1 is not here. So for symmetric, what should happen? If A is in relation to B, then B should be also in relation to A. If we take 1, 2 is here, then its counterpart, that is 2 1, should also be in R1. Since 1 2 is in R1 but 2 1 is not in R1, we can say R1 is not symmetric. Now for transitive, here we can see 1 2, this pair is in R1, also 2 3 is also in R1. If 1 2 is in R1, 2 3 is in R1, then 1 3 should have also been there. 1 3 should also be in this R1, but 1 3 is missing, so 1 3 is missing, is not in R1, because we have told this, if A is related to B and B is related to C, then A should be related to C, that is A is related to B, okay, B is related to C, but A is related to C, that is 1 is related to 3, which is missing here. So we can say R1 is not transitive. Okay, now let me rub this out. So this is for first question. Now second, we are being told the relation should be symmetric but neither reflexive nor transitive. So for that, let me take another relation R2, which contains elements, let us say it contains elements 1 2 and 2 1. It contains ordered pairs 1 2 and 2 1 only. Now this relation R2 is symmetric. Why it is symmetric? For symmetric, the condition is that if R2 is this, its inverse should be equal to R2. That is the inverse of R2, that is R2 inverse. So by inverse, what we mean? We swap the ordered pairs. So if we have 1 2, we can write 2 comma 1. In place of 2 1, we can write 1 2. Here we can see R2 is equal to R2 inverse. That is, if 1 2 is present, then its counterpart 2 1 should also be present for a relation to be symmetric. Okay, here we have seen that R is symmetric, R is symmetric. Okay, as I told you, if R is related to B, then it must be the case, that is, it must be the case that B should be also related to A for a relation to be symmetric. If we have 1 2, it is 1 is related to 2, and here we have 2 is related to 1, so we can say R is symmetric. For symmetric, the inverse of the relation should be equal to the relation itself, that is, here we have seen. So R is symmetric. Now what about is it transitive? So here we can see 1 belongs to set A. Okay, but 1 does not belong to R1. Sorry, R2 here. Okay, R is not reflexive. Here we can see 1 is in set A, but 1 1, this ordered pair is not in R2. That means R is not R is not reflexive. Okay, for a reflexive relation, what must happen? That is, every element must be paired with itself. Okay, so here 1 is present here, but 1 comma 1 is not present here, so we can say that 1 1 is not in relation R2, then R is not reflexive. Okay, for reflexive, what is the condition? Every element must be paired with itself, but other pairings are also allowed. But in R2 we have 1 2 and 2 1. 1 1 is missing, so it is not reflexive. What about transitive? Here we can see for transitive 1 2 belongs to R2. Okay, 2 1 also belong to R2. Here we can see. So if 1 2 belongs to R2, 2 1 also belongs to R2, then there must be the case that 1 1 must be in R2. That is 1 1 must be in R2, but 1 1 is not present in R2. Then we can say R is not transitive. That is, if this is A is related to B is related to C, then there should have been case that is A should have been related to C. So A and C is 1 and 1. 1 1 is not here present, so it's not transitive. Now let us take the third one, transitive but neither reflexive nor symmetric. So for that, let me take R3, the relation. That is, for this, let me take 1 2. Okay, if I take 1 2, let us take 2 3 also. 2 3 and 1 3. 1 3. Okay, now for is it transitive? Let us see. Here we can see 1 2 1 2 belongs to R3. Okay, 1 2 belongs to R3, and also 2 3 belongs to R3. Okay, and if 1 is in relation to 2, 2 is in relation to 3, then 1 should be in relation to 3, and 1 is, so we have 1 and 3, which is also present here in R3. That means R3 is transitive. Okay, that is, A is in relation to B, B is in relation to C, then there should be the case that A should be in relation to C, that is 1 3. We have also 1 2, 2 3 and 1 3, that is R is transitive. Let us find out whether it is reflexive or not. Here we can see 1 is in set A, 1 belongs to set A. Okay, but 1 comma 1 is not present in R3. Okay, as I have told you, for reflexive every element must be paired with itself, but other pairings are also allowed. So if we have here 1 2, it is allowed, 1 3 it is also allowed, 2 3 it is also allowed, but there should have been one relation, that is 1 1, which is not present here, because every element must be paired with itself, but other pairings are also allowed, but 1 is not paired with 1, so R3 is not what we call a reflexive. Okay, what about symmetric? So for symmetric, you can see 1 2 belongs to R3. Okay, so this 1 2, for this to be symmetric, its counterpart, that is 2 1, should also be present. 2 comma 1 should be present, but that is not in R3. That implies R3 is not symmetric. Okay. Now let us take the fourth one. Fourth one tells us find the relation which is reflexive, symmetric and transitive. Reflexive, symmetric and transitive. So for that, let me take here. Okay, so I will get lost of the space, so let me form a relation. So or let me write R4 here. So in R4, if I take the set of odd pairs, let me take 1 1 1 comma 1, then 2 comma 2, then 3 comma 3 3 3, then 4 4, one 2 2 1 1 3 and 3 1. Now I guess I have 1 1 2 1. Now let me rub this out. We have to show that it is reflexive, symmetric and transitive. So for that, let me take a relation that is R4 okay. So for that, let me take 1 2 will be there, 2 2 will be also there, and 3 3 will be also there. So 1 2 2 2, then we have 3 3 3 3 4 4, and if I take 1 4 and 4 1, okay, so it is getting hectic here. Now this is first we need to show it is symmetric. Or reflexive. So if it is reflexive, then every element must be paired with itself. So and with other elements also. So let me see here. So 2 is 2 2 we have here, 3 3 is 4 4 is okay. So it is, but there should be for reflexive 1 1 should also be there, okay, 1 comma 1, because for a relation to be reflexive, every element must be paired with itself, but other pairings are also allowed. So we have 1 1 2 2 3 3 4 4, and other pairings are also allowed. That is, we have 1 2 1 3 3 1 1 4 and 4 1. They are also allowed. So this is obviously what we call reflexive. It is reflexive. R4 is reflexive. Now what about symmetric? So for symmetric, we have told you if A is in relation to B, then there must be the case B should be also in relation to A. So let us take 1 is related to 1 and 1 in fact is related to 1. So we don't write we don't repeat, so we can write it like this: 1 1 and also 1 1. Okay, but repetition of elements in a set is not allowed, so we write only one ordered pair. So for here we have 1 2, okay. If we have 1 2, then I have to add another, that is 2 1. Okay, so 2 comma 1. So 1 2, its counterpart is 2 1. Okay, for 1 3 we have 3 1, 1 4 we have 4 1. Okay, so then it becomes so let me write it here. So we have 2 1 also here, 2 comma 1. So this R4 is reflexive, we have seen it. R4 is transitive, sorry, symmetric. Why? It is symmetric because if A is in relation to B, then it must be B is also in relation to A. If 1 2 is present, 2 1 is also present. If 1 3 is present, 3 1 is also present. 1 4 4 1 is also present. Okay, now what about transitive? Let us see if it is transitive. If I take this 1 2 is in R4, then 2 3 should also be in R4. We have not taken that very thing here, but if 1 2 is here, 2 1 we have also 2 1. Let us take 2 1, 2 1 here. Okay, 2 1 also belongs to R4. If 1 2 is in R4, 2 1 is in R4, then it must be that 1 1 should also be in R4. 1 1 should also be in R4, and we have written it here. So R4 is transitive also. Likewise, if I take 1 3 and 3 1, so 1 1 is present. 1 4 and 4 1, 1 1 is present. Okay, so it is also reflective, symmetric and transitive. Okay, sorry for the mistakes if I have encountered in this video, because it's blowing my mind here. Now we need to take a relation which is neither reflexive nor symmetric nor transitive. So for that, let me rub this out. Okay, so sorry if I have done any mistake here. You can also always rectify me. Three 1 4 comma 1, and then I have taken 1 2 and 2 1. I guess I remember it. Now let us take R5, a relation which is neither reflexive nor symmetric nor transitive. So for that, let me take the relation, that is, we have, let us take 1 2 1 2 and 2 3. Now it's not reflexive. For reflexive, if 1 belongs to one belongs to set A, then 1 comma 1 should also be in R5, which is not present here. that is, it is not reflexive. For reflexive, every element must be paired with itself, but other pairings are also allowed, so it's not reflexive. Now what about symmetric? So 1 2 is present, but 2 1 is not present. 1 2 belongs to R5, but 2 1 does not belong to R5. That means it is not symmetric. For transitive, if 1 2 belongs to R5, then 2 3, and if 2 3 also belongs to R5, then 1 2 and 2 3, that means 1 3 should also be the part of R5, 1 3 should also be a part of R5, but it is not present here. We can say it is not transitive here. Okay, now let's talk about functions. What is a function? A relation R from set A to set B is called a function. Okay, if I have two sets, first let me show it here. So let us say I have set A and I have set B. So a relation, if there is relation from set A to set B, is called a function if two conditions are satisfied. So every element of set A has an image in set B. No element of set A has more than one image in set B. Now let me explain. Let us suppose in set A we have the elements 1, 2, 3 and 4. And in set B, let us suppose we have elements 2, 4, 6, 8. Okay, let us explain it using the arrow diagram first. We are saying a relation from set A to set B is called a function. That is to say, a function is a special case of relation. By relation, what we mean, when we have a relation between the elements of two sets, we call that relation. So relation can be is less than, is greater than, is brother of, if there is some relation between elements of two sets, we call that relation. I have explained it in earlier videos, you can check them out. So for a relation R from set A to set B is called a function if two conditions are satisfied. That is, every element of set A has an image in set B. No element of set A has more than one image in set B. So let me show it here. Let us suppose 1 is in relation to 2 by somehow. Okay, so 1, there is a relation between 1 and 2. Now what I am saying here, I am saying if there is a relation between 1 and 2, I am saying 2 is the image of 1. Okay, so 2 is the image of 1, or I can say 1 has the image 2. Okay, so first thing is every element of set A has an image in set B. So 1 has the images 2. Let us suppose 2 has the image 4, 3 has the image 6, and 4 has the image 8. Okay, if here we have another element, let us suppose, we don't care about this. So first condition should be every element of set A has an image in set B. Here we can see 1 has the image, 2 has the image, 3 has the image, 4 has the image. So no element from set A is left without an image in set B. So this condition should be first satisfied. Now second condition is no element of set A has more than one image in set B. That is, 1 has only one image. It has no more than one image in set B. 2 has only one image. 3 has only one image, 4 has only one image. So I can say this is a function. If this is a function, let me give the examples which are not the functions. So let us suppose again I have set A. It contains elements 1, 2 and 3. Let us say 4. And I have here 5, 6, 7, 8, 9. So this is set B. Let us suppose here 1 is in relation to 5, 2 is related to 6, 4 is related to 7. Okay, is this a function? Now let us see. First condition is every element of set A has an image in set B. Has every element of set A an image in set B? 1 has the image, 2 has the image, but 3 is left without an image in set B. Clearly this is not a function. Now let us give another example. Let us suppose I have again set A and set B. Here we have 1, 2, 3, and here we have 4, 5, 6. Let us suppose 1 is related to 4, 2 is related to 5, and 3 is related to 5. Okay, is this a function? Let us see the two properties. Every element of set A has an image in set B. Yes, every element. 1 has the image as 4, 2 has the image as 5, 3 has the image as 5. So first condition is satisfied. Let us see second condition. No element of set A has more than one image in set B, but 1 has only one image, which is 4. 2 has only one image, which is 5. 3 has only one image, which is 5. So then is it a function? Yes, both conditions are satisfied. So this is in fact a function. Now let us see another example. Let us suppose we have the set A which contains elements 1, 2 and 3. We have set B which contains 4, 5, 6. So let us suppose 1 is in relation to 4, 2 is in relation to 5, and 2 is in relation to 6. And let us suppose here we have another one. Let us suppose 3 is in relation to 7. Let us see whether it is a function or not. Every element of set A has an image in set B. Here we can see every element has an image. 1 has 4, 2 has 5, 3 has 7. In fact 2 has 2 images here, 5 and 6. So first condition is satisfied. Every element of set A has an image in set B. So no element of set A is left without an image. So first condition is satisfied. Let us see second condition. No element of set A has more than one image in set B. This condition should be hold here. So 1 has only one image. 2 has two images. 5, the image of 2 is 5, the image of 2 is 6. Here 2 has two images here, 5 and 6. Clearly that is not possible for a relation to be a function. So this is not a function. Now let's take another example. Let us suppose we have set A contains 1, 2, 3 and set B contains 5, 6, 7. Let us suppose 1 is in relation to 6, 2 is in relation to 6, 3 is in relation to 6. Now let us see whether it is a function or not. See the properties. Every element of set A has an image in set B. Yes, every element of set A has an image in set B. 1 has the image 6, 2 has this image 6, 3 has this image 6. It doesn't matter whether they have the same image, but no element of set A is left without an image. So first condition is satisfied. Now let us see the second condition. No element of set A has more than one image in set B. 1 has only one image, which is 6. 2 has only one image, which is 6. 3 has only one image, which is 6. So clearly this is also a function. Okay. Why this was not a function? Because not all the elements of set A had an image in set B. 1 had this image 5, 2 had the image 6, but 3 was left without an image in set B. So this was not a function. Why this was a function? Every element of set A had an image in set B. So 1 has 4, 2 has 5, 3 has 6. And no element of set A had more than one image. 1 had only one image as 4, 2 as 5, 3 as 5. So this was a function. Why this was not a function? Although every element of set A had an image in set B, 1 has 4, 2 has 5, 2 has 6, 3 has 7, but the second condition was not met. That is, no elements of set A has more than one image in set B. 1 has only one image. Okay, no problem. 2 has two images here, 5 and 6. So this is not possible because the element in set A had two images in set B. Okay, so clearly this was not a function. Now in the fourth case, why this was a function? Because all the elements in set A had an image in set B. It doesn't matter whether they have one only same, it does not matter whether they have the same image, but every element had image. So first condition was met. And also no element of set A had more than one image in set B. 1 has only one image, 2 has only one image, 3 has only one image. That's why it was a function. Okay, now let's discuss about the domain and range of the function. Okay, so since this, so we can left out, this is not function, this was a function, and this was also function. What is domain? Let's denote by D subscript F. Domain of a function is the first set, whole first set. Okay, if this is a function, then domain is the whole first set. That is, here the domain of the function will be 1, 2, 3. That is 1, 2, 3. Okay, all the elements in set A which has the image in set B is the domain here. Okay, if it is a function, then all the elements of set A have an image in set B. So this is the domain of the function. So first it should be a function, then we can find its domain. Now here, since this is not a function, I cannot say that domain of this function because the functionality is not being satisfied here. Now what about the codomain? So codomain is whole second set. Okay, whole second set. So what are the elements in the second set? 4, 5 and 6. So 4, 5 and 6. Okay, what about range? Let's denote it by R subscript F. Range of this function F will be only those elements which are the images of the elements of set A. Okay, so in range we take only those elements which are the images of set A. So 4 is image of 1, so 4 will be in range. 5, yes, 5 is the image up to, so 5 will be in range, but 6 is not allowed here. Okay, 6 is not the image of any element. So in range we take only those elements which are the images of the elements of set A. Okay, now in this case, now you can see here domain of f, if this is a function, in fact this is a function, so domain is all the elements of set A, that is 1, 2, 3, 4. What about codomain? Codomain will be all the elements in set B, 2, 4, 6, 7 and 8. What about range? In range we take only those elements which are the images of the elements in set A. So 2, we take 2, 4, 6, 7 is not allowed because it is not the image of any element of set A, and we have 8. Okay, this defines our range here. We can also take another example. Okay, so let me rub this out to explain. So let us suppose we have A and B. Let us say A contains 1, 2, 3 and B contains X, Y, Z. So let us suppose 1 is connected to X, 2 is connected to X, 3 is connected to X. Clearly this is a function because every element of set A has an image in set B. Okay, no element of set A has more than one image in set B. 1 has only one image, 2 has only one image, 3 has only one image. Clearly this is a function. If this is a function, then domain of f will be all the elements in set A, 1, 2 and 3, 1, 2, 3. In codomain we take all elements in set B, that is X, Y and Z. Codomain will be X, Y and Z. Now what will be range? Range of this function will be only those elements which are the images of the elements in set A. So in range we have only X here. Okay, now let's explain it with the help of relational with the help of ordered pairs now. Okay, let us suppose X is a set which contains elements 1, 2, 3 and 4. Y is another set which contains 1, or let us take 2, 4, 2, 4, 6, 8 and 10. Let us suppose let us take the relation. Let us say let R1 is the relation, and in relation we have, let us suppose ordered pair 1, 2. We have 2, 4, then 3, 6, 3, 6 and 4, 8. We have to say whether this relation is a function or not. So if I use the arrow diagram, we have set X, we have set Y. So in set X we have 1, 2, 3, 4, 1, 2, 3, 4, and in set Y we have 2, 4, 6, 8 and 10. Now the relation is 1 is in relation to 2, so 1 is in relation to 2, 2 is in relation to 4, 3 is in relation to 6, 4 is in relation to 8. Is this a function? In fact, this is the function here. Why? Because every element of set A, here we have element of set X, has an image in set Y. Okay, 1 has image, 2 has image, 3 has image, 4 has image. And no element of set X has more than 1 image in set Y. So all the elements in set X have only 1 image in set Y. Clearly this is a function. Or we can say every element of set X is the first entry of some ordered pair. Okay, so every element of set X is the first entry. So this is first entry, this is first entry, this is first entry, this is first entry of ordered pair, and no two ordered pairs have the same first entry. So this ordered pair has only 1 entry. Okay, that is to say, since this is the ordered pair, each ordered pair, or what we say, every element of X is the first entry of some ordered pair, and no two ordered pairs have the same first entry here, if we talk about the ordered pairs. Now what is the domain of R1? Domain of R1 are all the elements of set X, all the first elements of relation here, not of set X. So domain of R1 will be all the elements, that is 1, 2, 3 and 4. So this is in fact a function. Codomain of R1 will be all the elements in set set Y. We have 2, 4, 6, 8 and 10. But in range we take only those elements of set Y which are the images of set X. So 2, 4, 6 and 8 only. 10 will not be included. So we have 2, 4, 6 and 8 here. Okay. Now let us take another relation here. Let us suppose we have another relation, that is from these two sets. The relation is, let us suppose 1, 2. We have 2, 4. We have 2, 10, and we have 3, 6. We need to find out whether this is a function or not. Okay, so in set X we have 1, 2, 3, 4 again. So let me write it again. 1, 2, 3, 4. We have 2, 4, 6, 8 and 10. 2, 4, 6, 8 and 10. Now what is the relation? So this is set X, this is set Y. So relation is here. 1 is in relation to 2. Yes. 2 is in relation to 4. 2 is in relation to 10. 3 is in relation to 6. Clearly this is not a function. Those two conditions are not met here. Every element of set A, here we have X, every element of set X does not have an image in set Y. Why? Because 1 has image, 2 has image, 3 has image, but 4 is left without an image. So this is not a function. Another thing is also violated. No element of set X has more than 1 image in set Y. 2 has here 2 images, 4 and 10. So clearly this is not a function. So this relation R2 is not a function here. Now So if this is not a function, we cannot take it as domain and codomain or range. Now let us learn some important pointers regarding the functions. A relation R from set A to set B is called a function. That is, a relation from set A to set B is called a function if two properties are satisfied. That is, every element of set A, if set A contains 1, 2, 3, and every element of set A has an image in set B. That is, if 1 is somehow associated with 4, 2 is linked to 5, 3 is linked to 6. That is, every element of set A should have an image in set B. That is, the image of 1 is 4, the image of 2 is 5, the image of 3 is 6. First condition. Second, no element of set A has more than one image in set B. That is, no element of set A has more than one image. That is, 1 has only one image, that is 4, 2 has only one image, which is 5, 3 has only one image, which is 6. If 3 has more than one images, if 3 has 6 as image and 7 as image, that is, if it has 2 images, then this does not correspond to a function. Okay. Now, how do we write the functions? Now, let us suppose f is a function from set A to set B. That is, this f is a function from set A to set B. It is denoted by, that is, f maps set A to set B, or we write f like this, A, that is, f maps set A to set B. Okay. Now, this set A is called the domain of function f, and it is denoted by df, d subscript f. So domain of the function is whole set A. That is, in this case specifically, domain of the function will be 1, 2, 3. So we have 1, 2, 3. This will be the domain. Now what about the codomain? Okay, the set B is called codomain of f. This set B is called codomain of function f. That is, codomain of f is whole set B. In this case, it is 4, 5, 6, and 7. Okay. Now, the unique element, let us suppose we have an element B in set B and element A in set A. Then the unique element B, which belongs to set B, associated by function f to an element A, which is in set A, and it is denoted by f of A. So B is equal to f of A and is called f image of A. So this B is called f image of A. In this case, what we call 4 is called f image of 1, 5 is called f image of 2. So we can write 4 can be written as, in this case, we can write in place of 4 as f of 1. So likewise, in place of 5, we can write f of 2. In this case, 6, which is f of 3. Now, this 4 is called f image of 1, or 4 is the image of 1 under f, or we call it simply 4 is f image of 1, 5 is f image of 2, 6 is f image of 3, and we write it like this: f of 1, f of 2, f of 3. In this case, the unique element B, which belongs to set B, associated by function f to an element A, which is in set A, is denoted by, we denoted by like this, f of A, and is called f image of A, or we also call it the value of A. And we write B is equal to f of A, which I have written here. So let me write it here. So B is equal to f of A. So this B is called F image of A, okay, and this A is called the pre-image of B, pre-image of B under F, obviously. Okay, no, you don't need to get confused. When I was saying that one has image 4, so in this case I am saying 1 is the pre-image of 4, 2 is the pre-image of 5, 3 is the pre-image of 6. Now for 4 I can write 4 is the F image of 1, 5 is the F image of 2, 6 is the F image of 3. Okay, so in technical words we say like this. Here A is called a pre-image of B under F. Now the set of all those elements in B which are the F images of at least one element in A is called the range of F. So range of F is the set of all elements, all those elements in B which are the F images of at least one element in set A is called the range of A. So here we can see 4 is the image of 1, 5 is the image of 2, 6 is the image of 3. Then in the range we will have only 4, 5 and 6. Okay, so range will be 4, 5, 6. The condition is that the set of all those elements in B which are the F images of at least one element in A. So this can be like this also. So if we have here 4, let us suppose 4 is also related to 6. Again this is a function because all the elements in set A are pre-images of the elements of set B. Okay, that is every element in set A has only one image in set B. Okay, and no element of set A has more than one image. 4 has only one image, 6, 3 has 6, 2 has, okay. So in a range we take only those elements which are the F images of at least one element in A, and we call it range of F. So 4 has F image, 5 has F image, 6 has the image or F image in A, but 7 has no image or F image in set A, so 7 will not be the part of range. Now if we also write like this. So if we have, let us suppose the ordered pair AB, if ordered pair AB belongs to a function F, what we call here, we call B is the F image of A, or B is the image of A under F. Okay, if this ordered pair belongs to some function F, then we say B is the F image of A, or B is the image of A under F. Now let us discuss about the types of functions. So first we have into function. If the function F which maps set A with set B is such that there is at least one element in set B which is not F image of any element in set A, that is to say F of A is not equal to B, then F is a function from A into B. So we have two sets, A containing 0, 1, 2, B containing 0, 1, 2, 3 and 4. We say this function is into function. Why? Because there are some elements in set B which are not F images of any element in set A. 0 is the f image of 0, 1 is the f image of 1, 4 is the f image of 2, but 2 and 3 are not f images of any elements of A. So we say this function is into function. We have taken an example. Let A contains elements 0, 1, 2, B contains 0, 1, 2, 3, 4, and we define the function that f matches or f maps set A with set B, defined by the function f of x is equal to x square. Then the set of ordered pairs for this function will be, so when we plug, in this case, when we plug in this function, when x is equal to 0, f of x will be 0 square. So when x is equal to 0, we will get 0 square, which is 0. When x is equal to 1, we will get f of 1 as 1 square, which is 1. Then when x is equal to 2, we will get f of 2 is equal to 2 square. So 2 square is 4. So what happens in case of into function? Range of the function is not equal to domain. In range, if I see here range of f, in range of f we have the elements 0, 1 and 4 only. In codomain, so let me write it here, CD, I don't have the space. In codomain we have 0, 1, 2, 3 and 4. Clearly in case of into function, range is not equal to codomain. Then we have the onto function, what we call surjective function. A function f which maps set A with set B is such that each element of B is the f image of at least one element in A, that is f of A is equal to B. Then f is a function from A onto B. That is to say, if we have set A and set B, if every element of set B is the f image of at least one element in set A, we say the function is onto function. Why? 0 is the f image of 0, 1 is the f image of negative 1, 1 is the f image of positive 1 also, 2 is the f image of 2. If every element of set B is the f image of at least one element in A, we say the function is onto function. We have taken an example. Let A contains negative 1, 0, positive 1, 2, B contains 0, 1, 2, and we define the function as f of x is mod of x. Then when x is equal to negative 1, so when x is equal to negative 1, when we have f of negative 1, we will get, in place of mod of negative 1 is positive 1, so we get negative 1, 1. So when x is equal to negative 1, f of x is positive 1. When x is equal to 0, similarly it will be 0. When f is equal to 1, f of x is equal to 1. When x is equal to 2, f of x will be 2. So in this case, what we see, range of f, range of this function f is in fact equal to the codomain, because in range we have 0, 1, 2. So here we can see, if I write it here, in range we have 0, 1 and 2. In codomain we also have 0, 1, 2. That means in case of onto function, range is equal to the codomain. Then we have one function, what we call injective function. If a function f which maps set A to set B is such that distinct elements of A have distinct f images in B, that is, if x1 and x2 are elements in set A such that x1 is not equal to x2, then f image of x1 is not equal to f image of x2, that is f of x1 is not equal to f of x2. Then the function is called to one function. Here we can see 1 has only one is the f image of 1 only, 4 is the f image of 2 only, 9 is the f image of 3 only. Then we say it is one function when distinct elements in set A have distinct f images in set B. The function is said to be 1, 1. So what is the difference? Or we in onto function we have seen that -1 and +1 have same image in set B, but here distinct elements have distinct images. Then the function is called 1, 1 function. Now we also call this injective function. We have taken the example if A contains 1, 2, 3, B contains 1, 2, 3, 4, 9, and if we define the function f of x is equal to x square, clearly here f of 1 will be 1, so 1 square is 1, f of 2, that is 2 square is 4, f of 3 is 3 square is 9. So distinct elements have distinct f images in case of 1, 1 function. Then we have many one function. A function is said to be many one if 2 or more elements in set A have the same image in set B. Okay, that is to say, if f maps set A to set B, we say it is many one function if there exists x1 and x2 which belong to set A such that x1 is not equal to x2 but f of x1 is equal to x2. So we have explained it with an example. A contains -1, 0 and 1, B contains 0 and 1. Now in A we have 0, -1 and +1, B contains 0 and 1, and we define the function f of x is equal to x square. Now here when we plug, f of 0 will be 0, but f of -1 will be equal to 1, and f of +1 is again 1. Here -1 is not equal to +1, but f of -1 is equal to f of +1, which is equal to 1 here. So when, in short, when 2 or more elements in set A have same image in set B, we say the function is many one. Lastly, we have 1, 1 onto function, or what we call bijective function. Now a function is said to be 1, 1 onto or bijective function if it is both surjective function, that is it is onto function, and it is also injective function. So example, we have taken f of x is equal to 2x. Okay, so if set A contains 1, 2 and 3, set B contains 2, 4, 6, 1, 2 is f image of 1, 4 is f image of 2, 6 is f image of 3. What happens here? Each element of set B is f image of elements in set A. Okay, 2 is the f image of 1, 4 is the f image of 2, 6 is the f image of 3. So we don't have any element in set B which is not f image of any element of set A. Okay, so this is 1, 1. Sorry, this is first onto. And why it is 1, 1? Because distinct elements have distinct f images in set B. 1 has 2, 2 has 4, 3 has 6. Okay, so when a function is both 1, 1, by 1, 1 we mean distinct elements have distinct f images, and when we say it is onto, we say that every element in set B is f image of at least one element in set A. Okay, so these were the types of functions. Now let us briefly discuss about the types of functions. First we have into function. A function is said to be into function if there is at least one element present in set B which is not f image of any element in set A. Here 0 is the image of 0, 1 is the image of 1, 4 is the image of 2, but 2 and 3 are not the f images or simply the images of the elements present in set A, so we say the function is into function. Then we have onto function, we call it surjective function also. A function is said to be surjective if each element of set B is the f image of at least one element in A. That is 0 is the image of 0, 1 is the image of two elements, that is -1 and +1. It doesn't matter if 1 is the image of two elements present in A, 2 is the image of 2, but the thing is here that all the elements present in set B should be or must be the f images of the elements present in A. Okay. Then we have one function, we call this injective function also. A function is said to be one function if distinct elements in set A have distinct images in set B. Okay, so no two elements in set A have same image in set B. Here 1 has the image 1, 2 has the image 4, 3 has the image 9. Okay, so we say this is one function when distinct elements in set A have distinct images in set B. Then we have many one function. So a function is said to be many one function if two or more elements in set A have same image in set B. That is, the image of -1 is 1, the image of 1 is 1, so two elements in set A have same image in set B, then we say the function is many one function. Lastly, we have one onto function, what we call bijective function. A function which is both one and onto, we say the function is bijective function. Now if I take this set A and set B, 2 is the image of 1, 4 is the image of 2, 6 is the image of 3. That is, distinct elements in set A have distinct images in set B. That is, it is 1. Why this is onto function? Because all the elements present in set B are the f images or images of set A. So there is no element in set B which is not the image of the element present in set A. That is why it is onto also. Let's discuss about the inverse of a function. Consider a bijection function, that is f maps set A to set B. Set A is ABC, set B is XYZ. Since f is 1, distinct elements of A are taken to distinct elements of B by f. Also f is onto, that means every element of B has pre-image in A. Now let me explain this step. So if we consider a bijection function or bijective function. Now if a function is bijective, then it must be one function, one function. It must be first 1 and it should be also onto function. By 1 what we mean? Distinct elements of set A have distinct images in set B. That is, element A has X as image, B has Y, C has Z. So distinct elements have distinct images. Okay, no two elements have same image in set B. So this function is 1. Now what is meant by onto? So if a function is onto, we mean that every element of set B has pre-image in set A. Every element, that is, X has the pre-image A, Y has pre-image B, Z has pre-image C. Now if I put another element here, okay, then in this case this function does not hold as onto function, because x, y and z have pre-images but w does not have pre-image, although it is one function but it is not onto function. Okay, so when we consider a bijective function which is 1 and onto, okay, when we combine these two results, that means for let us suppose B is an element in set B. Okay, I am not taking this into consideration now. Let us suppose for B belongs to set B, there exists one and only one, that is A element which is in set A, such that f of A is equal to B. So if you are getting confused, let me explain. If we have a bijective function which is 1 and onto, then for any B belongs to set B, there exists only one and only one element A which belongs to set A, such that f of A is equal to B. Now let me explain it with an example. Let us suppose we have set A, it contains 1, 2 and 3, and set B contains 4, 5, 6. Okay, since it is bijective, we will have this kind of relation. Now what I am saying, for B belongs to set B, let us take this B element as 4. So we write here, if 4 belongs to set B, there exists only one and only one element, which is here 1, obviously 1, which belongs to set A, such that f of 1 is equal to 4. Okay, now it cannot be case that f of 2 is also equal to 4. So it is not, it should not be the case that f of 2 should also be equal to 4, or f of 3 should not be equal to 4, because why? It is bijective, distinct elements have distinct images in set B. So this is meant by that for B belongs to set B, there exists A element in set A such that f of A is equal to B. So this condition should hold here. Now so thus by a function f inverse which maps set B to set A, defined by f inverse B is equal to A if and only if f of A is equal to B. Now on the arrow diagram, what happens here? Set A is ABC, set B is XYZ. If it is F, its F inverse will be that we swap the elements, or we swap the sets. That is, here we have B, we write the B set first, then A set, then we map them. Okay, in case of the arrow diagram. Now if we are being given a function in terms of ordered pairs, let us suppose we have a function f is being given us as ordered pairs, or let us take the ordered pair here. So we have ax, by and cz. Okay, then its f inverse will be, we interchange the elements in the ordered pair. So we write first xa, here by we write yb, and here cz we write zc. That will be the inverse if we are being given the function in terms of ordered pairs. Now if the inverse, now if the function is represented by, if we have a function, let us suppose if a function is represented by an equation, let us suppose f of x is equal to 2x plus 3. How do we find its inverse? So what we do, first we write in terms of f, in place of f of x is y. So first step is we write y is equal to 2x plus 3. Then what we do, we interchange y with x. So in place of y we write x, and in place of x we write y. So here it is x, we write y. Then we solve for y. So 2y will be equal to x minus 3, dividing both sides by 2. Y will be equal to x minus 3 divided by 2. Okay. When we solve for y, then we replace y with f inverse x. So in place of y we write f inverse x, which will be equal to x minus 3 divided by 2. So this is how do we find out the inverse if we have an equation. Let's learn about the composition of functions. Let f is a function which maps set A to set B, and g be another function which maps set B to set C. Then composition of f and g is denoted by GOF, g small o f. Okay, so it's like this: g small circle f, we call it g of f of x, or GOF here is a function from A to C given by, that is GOF is equal to, GOF is a function which maps set A to set C such that GOF x is equal to g of f of x for all x belongs to A. Okay, now if f is a function from set A to set B and g is a function from set B to set C, okay, then GOF is, so what is GOF? GOF related set A with set C. So here if we have A element, it will become f of A. Okay, so this f of A is the pre-image of element A. Now when we have f of A here, okay, now this is the pre-image of this g of f of A here. Okay, so we have from A to B is f function, from B to C we have g function, then from A to C we will have g of f of A. Now if you are getting confused, let me give an example. Let us suppose that f be a function which relates which maps real numbers with real numbers from R to R, okay, and g be another function which also maps real numbers with real numbers from R to R. And let us suppose f of x is a function, that is f of x is equal to 2x such that x belongs to real numbers. Okay, this is not the relation symbol here. And let us suppose g of x is another function which is, let us suppose x square, okay, such that x also belongs to real numbers. Okay, then what will be the GOF? Then g of f, what we call GOF, or let me put it bracket, g of f of x can be written as g of f of x. Okay, so what we do here now, since f of x is 2x, we need to find g of f of x here. Okay, so what we write, we know that f of x is 2x, so can we write g of, what we call, or let me put it into the brackets not to get confused with the multiplication. So g of f of x. Now since f of x is 2x, okay, then g of 2x, so in place of x we write 2x in this function. So we have since g of x is x square, so g of 2x will be equal to, g of 2x will be equal to, so we have in place of x we write 2x, so we have 2x square, which is equal to 4x square. Okay, so g of what we call GOF of x comes out to be 4x square. Okay, now if you are getting confused, let us form it is fog also, that is f of or FOG. f of g of x. Okay, now what will be the fog here? So can I write fog like this? F of g of x. Okay, so we have f. What is g of x? See, g of x is x square. So can I write x square? Now f of x square. Since f is equal to 2x, so we have, sorry, f of x is 2x. So in this place x we write x square. So we have it will be equal to 2 times, in place of x we write x square. So that will be our fog here. Okay, this is how do we form the composition of two functions. Let's learn about identity function, even function, and odd function. The identity function of a set A onto itself is denoted by I subscript A and defined as I is a function of x which is equal to x for all x belongs to set A, or simply f of x is equal to x. That is to say, if we have set A contains A, B, C, okay, and we have set B, let us suppose it contains A, B and C. Now this A is mapped with itself, B is mapped with itself, C is mapped with itself. That is, this is our identity function. If we have f of x is equal to x, so f of x is equal to x for any value of x. So if we have f of 1 will be equal to 1, f of negative 1 will be equal to negative 1, so f of 2 will be equal to 2. So if I write it here, so if A contains 1, negative 1, or let me write 1, negative 1 and 2, so what will be the set B? Set B will be again 1, negative 1 and 2. That means this is the identity function here. Okay, now we have the even function. A function f of x is said to be even if f of minus x is equal to f of x. For example, we have, let us suppose we have a function, let us suppose f of x is equal to x square. Okay, now if I write f of minus x, so in place of x we have minus x, so we have minus x square, it will become x square. Okay, so f of x is x square, f of negative x is also x square. That means f of negative x is in fact equal to f of x. Why? F of negative x is x square and f of x is also x square. So a function is said to be even if f of minus x is equal to f of x. Now we have the odd function. A function is said to be odd if f of minus x is equal to minus times f of x, where f is the function. Let us suppose we take a function, let us suppose, if I have the space here, so let us suppose f of x is our function, x plus 1 upon x, and we put here condition that x should not be equal to 0. Okay, division by 0 is not allowed. Okay, I am saying that this function is odd function. Why? If I write f of negative x, so every place I will write, in place of x we have negative x, so we have negative x, then plus 1 divided by negative x, and it can be rewritten like this: negative x minus 1 upon x, or let's take minus common, we are left with x plus 1 upon x, which is equal to negative times what is x plus 1 upon x? It is our original function, which is f of x. That means if f of x was this, f of x is x plus 1 upon x, then f of negative x came out to be negative f of x. So here we can see f of negative x came out to be negative times f of x. So we say this function is odd function. Now there are times that is every function need not to be even or odd. Okay, so if we have a function f of x is equal to x plus 1, it is neither even nor odd. Why? So if I have this space, let me form this space, because here f of negative x, if I plug here f of minus x, so we'll get minus x plus 1, so which is not equal to this f of x. Okay, also if I take f of negative x, f of negative x is negative x plus 1. Okay, so it is also not equal to negative times f of x. Okay, so this kind of function is neither even nor odd. Now let's learn about the description of a function. Suppose f is a function which maps set A to set B, such that set A consists of finite number of elements and B is a set which contains real numbers. Then f of x can be described by listing the values which it attains at different points of its domain. That is to say, if we have a function f which maps set A to set B and A is finite set, let us suppose A contains elements negative 1, 1, 2 and 3 and B is the set of real numbers, then the function f from A to B can be described as, that is, when x is equal to negative 1, so when x is equal to negative 1, f of negative 1, let us suppose it is equal to 3. Likewise, when x is equal to 1, f of 1 is 0. We don't know how, but let us suppose. Likewise, when x is equal to 2, we get f of 2 as 1 upon 2, and when x is equal to 3, f of 3 is equal to 0. Now, in this case, what happens when A is finite? So we can write the function in roster form also, that is, we can write the ordered pairs here, that is, negative 1, when x is negative 1, f of negative 1, which is y, which is 3, so we will get 3. Likewise, when x is 1, f of 1 is 0, and when x is 2, f of 2 is, let us suppose, 1 upon 2, and when x is 3, let us suppose f of 3 is 0. Now here, when the domain of the function was finite, that is, when A was finite set, we can list all the values of the function. Okay, this is how do we write it. But what happens when A is infinite? Then we cannot list all the elements in this roster form. Okay, if A was infinite, then can we write the function in this form? No, obviously we cannot write, because if A is infinite, domain is infinite, then we cannot list all the values of the function in this form. Then what happens there? So that is what we have written here. Here, in case A is infinite set, then f cannot be described by listing the images at the points in its domain. So for that, here let us suppose set A, here we have set B. If set A is infinite, we have negative 1, 2, 3 and so on, and B is, let us suppose it is also infinite, negative 1, 2, 5, 7. Now if I want to list them in this fashion, a roster form, so I cannot write all the ordered pairs here. It is impossible to write all those, because A is infinite, B is infinite, so we cannot write the function in this roster form, or we cannot list the value of the function at the different points on its domain. Having said that, then what will we do then? In that case, in such cases, functions are generally described by formula. So we use a formula to describe a function. That is to say, The example, let us suppose f is a function which maps integers to integers, okay, z to z, given by f of x is equal to x square plus 1. Then we write the function in this form, okay, that is f of x is equal to x square plus 1, or any let us suppose x raised power 5 plus 1, or x upon 2, or we can write a function f maps real numbers to real numbers given by f of x is equal to x square. So in this case, when it is not possible to list all the elements, so list all the values of a function at different points in its domain, then we write the functions generally using a formula, okay. Till now we were we were assuming that both set a and b were finite, then we were solving the functions. But more generally we use the formulas to describe the functions. When the domain of a function is infinite, then we have to use the formula. Let f of x be a real valued function. All the values of x for which f of x is defined is called domain of a function. Now let me explain it in detail. When we say f of x be a real valued function, we mean this function f of x takes only real values. We know that there are two types of numbers. We have two types of numbers. We have two types of numbers. We have the real numbers, and we have the imaginary numbers. So in real numbers, it consists of the set of rational and irrational numbers, like we have 1, 2, 0, -2, 5 upon 3, -2 upon 3, or we have under root 2, under root 5, we have pi, we have 1 upon under root 3, etc. These are all called the real numbers. Now, by imaginary numbers, we mean the numbers which are in the form of b times I, where b is the real number and I denotes the iota. We call it root of a -1. So if we have the numbers in this fashion, that is -3, -5, -7, or root of any negative number, these are all called imaginary numbers. When we say f of x be a real valued function, we mean f of x takes only real numbers, okay. Having said that, now what is domain? So all the values of x for which f of x is defined, what we say, you can think of x as the input and f of x as the output. Then what is meant by this? All the values of input for which our output is defined is called domain of a function. So by defined, what we mean? We mean when we plug the input into a function, and if our output is a real value, or our output our answer is a valid answer, valid output, okay, we call those very values of x as the domain of a function, okay. Now let me explain with an example. Let us suppose f of x be a function. Let us suppose we have x square plus 1, okay. We have to find out the domain of this function. Now you can think of x as input and f of x as output. Let us suppose we have x here and we have f of x here. Now if we plug any value of x, let us suppose x is 1, so f of x will be x square plus 1, or we write here 1 square plus 1, which is 2. If I plug x is equal to 0, we will get 0 square, because f of x is x square plus 1. So we get 0 square plus 1, which is equal to 1, or if x is equal to -1, we will get -1 square plus 1, and our f of x will be square of a negative number is positive, so we will get here 1 plus 1, which is again 2 here. Likewise, you can put any value. Let us suppose 2. Here we will get 2 square plus 1, which is equal to 2s are 4 plus 5. Now, when we say all the values of x, so all the values of x for which our output, so you can think of x as input and f of x as output, okay, for which our f of x is defined, then all those x's, the values of x's, are called the domain of the function. Here you can see when we plug 1 we get 2, okay, so 2 is real output. When we plug 0 we get here 1. When we plug -1 we get 2. So our output f of x, it is a real value, it is a real number here, okay. So in this case, in this example, what will be the domain of this function? Okay, so this function will take all the real values, okay. So we don't have any restriction on the domain. All the real numbers are the domain of this function, because we can put any value, any real number here, and our output will be also real number, okay. So we can say domain of this function, domain of f, is all real numbers, okay. Now we can write domain of f like this, d subscript f also in this fashion. So domain of f, we can write it in the interval notation is also. So we take the open interval and write negative infinity to positive infinity. So from negative infinity to positive infinity, it shows us the set of real numbers or real number. So from negative infinity to positive infinity will be our domain of the function, or we simply say domain of this specific function is the set of all real numbers, okay. Now let us take another example to explain this. Let us take another example. Let us suppose f of x, we have a function in this form, that is f of x is equal to 1 upon x, and we are supposed to find out the domain of this function, okay. Again, let's write here x, and let's write it here f of x, okay. Now plug the values here. When x is equal to, let us suppose 1, f of x will be 1 upon 1, which is equal to 1. Let us plug x is equal to 0. So we will get f of x will be 1 divided by 0. But we know that division by 0 is not allowed. So 1 divided by 0 will be undefined. Now if I plug any value of x, let's suppose -1 here. So we get 1 divided by -1, which is equal to -1. Any number we can put here, okay. Let us suppose 3, we will get 1 divided by 3. So we have 1 upon 3. Now the domain of this function, as you can see, are all real numbers except this 0. When we plug 0 as input, our function becomes undefined. That was the definition of the domain, that is all the values of x for which f of x is defined is called the domain of a function. Now this function is not defined when the value of x is 0. So what will be the domain of this function? So domain of this function will be the all real numbers except 0, because 0, if we put 0, so the function is undefined. We don't get a real value here, because 1 upon 0, it is not a real number. In interval notations, how do we show it? So let me draw a number line first, okay. So number line is from negative infinity to positive infinity, we know. Now let us suppose 0 is here, Okay, in interval notations we can show, we can write the domain like this. From negative infinity we put the open interval here, negative infinity to 0, because we are not including 0 into domain. That's why we are taking this open interval or this bracket, round bracket, union from 0 to positive infinity. That will be, if we write a domain in this fashion or in this fashion, it is same, from negative infinity to 0 excluding 0, union, and from 0 to positive infinity. And here we also take the open brackets or round brackets, because we are not including 0 here. So when we plug this, if we have like this 0 to infinity, let us suppose if I put these this bracket, square bracket, that means we are including 0. When we put this round bracket, that means we are excluding this 0. That's why we have put here this round bracket. Okay, now why are we putting a round bracket to negative infinity? Because infinity is not a number. Okay, so it shows us unboundedness. That's why we put open interval here. It is not a number, so that's why we are taking this open interval here. This is how do we show the domain of a function. Now let us be very clear. What are the restrictions? What should we take into account when we are trying to find out the domain of a function? So first thing is that if we have a function, let us suppose y is equal to f of x. Okay, now first thing is we should keep in mind, that is the denominator of a function should not be 0. That is denominator should not be equal to 0. First thing. Okay, second thing is that if we have a function, or if we have an expression under root of an expression, it should be also greater or equal to 0. Now if this expression is in numerator, okay, so if this expression is in numerator, if the expression is in numerator, that is if we have like this x square plus 2, let us suppose, upon 3. So in this case what should happen? This expression x square plus 2 should be greater or equal to 0. Then if the expression is in denominator, so if we have 1 divided by like this the expression, then two things should hold. First, this whole term should be not equal to 0, as we have shown here, that is denominator should not be equal to 0, and this expression should be greater or equal to 0. That means these two conditions are simultaneously to be put here. That is, first, this whole expression, that is this under root expression, it should not be equal to 0. Then the expression itself, this expression itself, it should be greater or equal to 0. That means if we have the expression under root of an expression in the denominator, that means in this case we should have the expression should be strictly greater than 0, because two conditions are here to be met. First, denominator should not be equal to 0. Okay, then second is that the expression should be greater than or equal to 0. Now let's learn some rules for finding domain of a function. To find out the domain of a function, we should keep some rules in mind. So first rule is the denominator of a function should not be equal to 0. So we exclude all those elements from the domain which makes the denominator of a function equal to 0. Okay, that is, if we have 1 divided by x minus 1, let us suppose it is a function. So what will we do? First rule says us that x minus 1 should not be equal to 0. So we exclude those values which make the denominator 0. Okay, so in this case, first, so for f of x to be defined, so the denominator, that is x minus 1, should not be equal to 0. So that means x should not be equal to 1. Okay, if I transpose it here, so it will become positive 1. That means the domain of this function, that is domain of this function, will be all real numbers except 1. Okay, or in interval notations we can write it like this. If I draw, if 1 is here, we have negative infinity here, positive infinity here. So in interval notations we will have from negative infinity, open interval, negative infinity, then we have 1, and we have open interval. Why? Because we are excluding 1 from the domain, and from which is our union here, from 1 to infinity. Again 1 is not included, so we can write it like this. This will be the domain of this very function. So rule number 1, denominator should not be equal to 0. Let's take another example. Let us suppose we have a function f of x is equal to, let us suppose x square plus 3x divided by x square, let's take minus 5x plus 6. Let us suppose this is our function and we want to find out its domain. Again, the first rule, denominator should not be equal to 0. So in this case, for f of x to be defined, the denominator x square minus 5x plus 6 should not be equal to 0. Okay, since this is a quadratic function, let us solve it here first for equality, for the sake of simplicity. Okay, so we have x square minus 5x plus 6 is equal to 0. So if we find out the values which makes this equation or this expression equal to 0, then we will exclude those very values. Since this is the quadratic equation, so we will use the splitting the middle term method. That is, the sum of the two numbers should be such that it should be equal to the coefficient of the middle term, which is -5, and the product of the same two numbers should be equal to the constant term, which is 6. Now we can use our brain here, obviously. So we can think of the numbers here. So we have, if I put -3 and -2 here, so -3 plus -2 is -5, and -3 times -2, so negative times negative is positive, 3 into 2 is 6. Okay, so we got the values here. That is, if I write this quadratic equation like this, so we have x square. In place of this middle term, I can write, in place of minus 5x, I can write minus 3x minus 2x, and in place of 6 I can write negative 3 times negative 2, so I can write negative 3 into negative 2 is equal to 0. Okay, now let us factor out x from the first two terms. So if I factor out x, we are left with x minus 3, and let us factor out negative 2 from the last two terms. So this is only one term here, so if I factor out negative 2, we will be left with x minus 3, and we set it equal to 0. Now let us factor out x minus 3. If I take x minus 3 and x minus 3, we are left with x minus 2 should be equal to 0. That implies either x minus 3 is equal to 0, which will give us x is equal to, transpose this, it becomes plus 3, or x minus 2 is equal to 0. Either this is 0 or this is 0, which implies x is equal to, transpose it here, it becomes plus 2. So the values of x which makes this denominator equal to 0 are 2 and 3. Okay, so we can say that here the domain of the function will be all the real numbers, or let me write it here, that means x cannot be equal to 2, and x cannot be equal to 3. All real numbers except 2 and 3, that will be the domain of this very function. Okay, so we exclude all those values of x which makes the denominator equal to 0. There were only two values, 2 and 3, which were making denominator 0. Now how do we write it in interval notation? So let me write it like this. We have negative infinity to positive infinity. Okay, so let us say this is 2 here, and here we have 3. So in interval notations, we have to take the open interval from negative. Why we are taking open interval with infinity? Because infinity is an idea. It shows us unboundedness. It's not a number. That's why we are not including this infinity here. Okay, from negative infinity to 2, because we are excluding 2, so we put this open interval. Then we have union, then from 2 to 3, that means 2 to 3. Again we are taking the open interval, because 3 is also not included, neither 2 nor 3, but the numbers between 2 and 3, they are included. Then we take union from 3 to infinity, again 3 to infinity. That will be the domain of this very function. Okay, now let us solve some other questions here. Or before we solve some other questions, let us explain rule number 2 and 3. So rule number 2 is that under root of an expression, the expression which is under the root, it should be greater or equal to 0 if this under root expression is in numerator. Okay, and rule number 3 is that the expression which is under this root, it should be strictly greater than 0 if it is in the denominator. So rule 2 says us if we have a function, let us suppose x minus 2. Okay, so for this function to be defined, this x minus 2 should be greater or equal to 0. Why we are putting this restriction? Only because if it were a negative number, then we will get under root of a negative number, which is not the real number, which is in fact the imaginary number, which we have already discussed. So we are talking about the real valued functions where our domain is real. Okay, that's why we are putting this restriction here. So the expression under the root, it should be greater or equal to 0 if it is in the numerator. Rule 3 says us that if this expression is here, let us suppose in the denominator, under root expression is in the denominator, then what should happen? There will apply two rules. First, that is denominator should not be equal to 0. That means this whole expression or this term should not be equal to 0. And second condition is that this term x minus 2, it should be greater or equal to 0. Now if we combine these two rules, that means we should get the strict inequality. That means the expression under the root which is in the denominator, it should be strictly greater than 0. Okay, now let us take it one by one. Let us take a question. Let us suppose f of x, we are talking about the first rule here. Let us suppose we have a function, any function. Let us take, let us say f of x is under root x minus 1. Now for this function to be defined, let's write for this function to be defined, what should happen? This expression which is under the root x minus 1, so this expression should be greater or equal to 0. That means x should be greater or equal to, transpose this here, it becomes 1. That means domain of this function will be, so domain will be, so we include 1 here, so we put open interval here, closed interval. That means we include 1 and our domain will be from 1 to infinity here. Okay, this is for rule 2nd. Now what about rule 3rd? Let us suppose f of x is a function like this. We have 1 divided by under root of 1 minus x. Now since the under root is in the denominator, the expression under the root, it should be strictly greater than 0. That means for f of x to be defined, that means 1 minus x, that means this term should be strictly greater than 0. Or we can write 1 should be greater than, transpose it here, it becomes x, positive x, or which means x should be less than 0. In this case, domain of the function, domain of f of x will be, so x, so if here it is 0, x should be less than 0. So domain will be from negative infinity to 0. So we will have negative infinity sorry, here it is x should be less than 1. Okay, from negative infinity to 1. So we don't include 1 here because we have strict inequality here. Okay, now let's take another case, another question, rather a more hard question. So let us suppose if we have f of x is equal to, let us suppose we have x minus 1 divided by 2 minus x. Okay, so let's take 2 minus x here. Now we need to find out the domain of this function. Now here first thing is that so this expression, this is if we consider it only numerator, so this rule should be held here. That means this should be greater or equal to 0. But for x minus 1 upon 2 minus x, this should also be not equal to 0. Okay, so for this function, because if it is 0, so it will be undefined. So we will get under root of x minus 1, let us suppose 0, so it will be x minus 1 upon 0, it is undefined. So under root of undefined is in fact undefined. So first thing is that in this case 2 minus x should not be equal to 0. So that means 2 minus x should not be equal to 0. That implies x should not be equal to 2. Okay, see carefully. Now we know that from the second rule that this whole expression should be greater or equal to 0 for this function to be defined for its domain. Okay, so that means for f of x to be defined x minus 1 upon 2 minus x, it should be greater or equal to 0. Okay, now here mostly what people do, they do the cross multiplication. That is, they do like this, x minus 1 transpose this here, so it becomes 0 times 2 minus x, or x minus 1, 0 times anything, it is 0. So x minus x is equal to transpose it here, it becomes 1. Okay, but this is absolutely incorrect. We cannot do this because we have the inequality here. Now how do we find out the value which makes value of x which makes this whole expression positive or greater or equal to 0? So we need to find out x minus 1 divided by 2 minus x, it should be positive. Okay, now we can do one thing. Is there a way that our denominator becomes positive first? Then it will be very easy to solve for numerator. Let us see. If we do one thing, if we multiply and divide by the denominator, that is 2 minus x here, and we multiply here also with 2 minus x. Okay, so what will happen? We will get x minus 1 times 2 minus x divided by 2 minus x whole square. Remember why we are doing this. So for this expression to be positive, either we should get numerator positive and also denominator positive, or we should get numerator negative and denominator negative, then this whole term will be positive. Either we should get both numerator and denominator positive. For this expression to be positive, or both numerator and denominator should be negative, so that this whole expression negative negative gets cancelled. This expression becomes greater or equal to 0. So what we want to do here, what we have done here, we had made denominator greater than 0. Why? Now square of any real number is positive. If I take 2 minus, let us suppose we have already excluded 2 from this, so we cannot take 2. Let us say 2 minus 3 square, which is negative 1 square. So square of any real number is positive. Square of, in fact, any number is positive. We know that very thing. So here our denominator is positive. Okay. Now we need to think of this numerator expression. When will be it positive? Okay. For that, what will we do? For that, let me draw the, again this interval notation. Now let us partition this interval here. So since x minus 1 and 2 minus x, so if x is equal to 1 and x is equal to 2, let us suppose x is here 1, x is here 2. Okay, so we partition it like this. So here we have negative infinity, here we have positive infinity. So see carefully, since we want this numerator to be greater or equal to 0, we want it positive. Let us see the values between the pointers on this number line. So if we take a number to the left of this one, let's take to the left of 1, it will be 0. Let's take 0. Okay, so what will happen to x minus 1 and 2 minus x for this to be positive? Okay, so if I put x, the value of x is 0, so it will become 0 minus 1 times 2 minus 0. So we get here 0 minus 1 is negative, and 2 minus 0, it is positive. So negative times positive, it is negative. But we want our this numerator to be positive, so it is here negative. Now what is between 1 and 2? Okay, let's take any number between 1 and 2. So for that, let me rub this out again. So we have x minus 1 and 2 minus x. So between 1 and 2, let's take 1.5. So if we have, in place of x is 1.5 minus 1, then we have 2 minus 1.5. Let us see what sign we will get. 1.5 minus 1, it will be 0.5. 2 minus 1.5, it will be also positive. So this is positive, this is positive. So between 1 and 2, we are getting the positive. The value of this expression is positive. Now what about the values between 2 and infinity? Let us take the values between 2 and infinity. Let us put any random number greater than 2. So let's take 3. So we have here 3 minus 1. Here we have 2 minus 3. 3 minus 1, it is positive. 2 minus 3, it will be negative. So again, positive times negative, it is negative. Okay. So what will be our domain in this case? Our domain is defined only between 1 and 2. This part is excluded. Why? Because we are getting negative, so we are getting this expression is negative, and this part is also excluded, because for this part also we are getting this expression is negative. Only this part gives us the positive value. So domain of f, domain of this function will be equal to, now let us see whether we have to include 1 or not. Now if we plug here 1, so 1 minus 1 is 0, 2 minus 1 is 1, so we will get here 0. So we don't have any problem with 1, so it is to be included in the domain. Now what about 2? We have already discarded it. We cannot take 2 here, so here we will have the open interval. That will be the domain of this very function. Let's take some other examples. Let us suppose we have the function f of x is equal to under root of 16 minus x square. Okay, since this expression or this term is in the numerator, so for f of x to be defined, what should happen here? 16 minus x square, the expression under the root, it should be greater or equal to 0. Okay, so 16 can be written as 4 square minus, then we have x square, it should be greater or equal to 0. That means we can write it like a square minus b square. So if we have a square minus b square, we know it is equal to a minus b times a plus b. Likewise here we have 4 minus x times 4 plus x, it should be greater or equal to 0. Having said that, now again we need to use partition our interval. So for that, where do I put the interval notation? Let's put it here. So we have from negative infinity to positive infinity. Okay, so let's put the value. So x minus 4, so let's put x is equal to negative 4 and x is positive 4 here. So we have here, let us suppose negative 4, and here let us suppose we have positive 4. Okay, now since we want this expression to be positive, let us find the values between the partitions on this number line. Now to the left of negative 4, if I put any value of x, let us suppose x is a negative 5. So what will be then? 4 minus x, 4 plus x. If I put a number to the left of negative 4, which is negative 5, so we'll get 4 minus 5. Here we will get 4 minus 5. So here we will get 4 plus 5, and here we will get 4 minus 5, which is negative 1. So here it is positive, here it is negative. So positive times negative is negative. So to the left we are getting negative. This whole expression is negative. What about between negative 4 and positive 4? So we have 4 minus x times 4 plus x, and we want it to be positive. So let us plug a number between negative 4 and positive 4. So we can think of 0. So we have here 4 minus 0 is 4. Then 4 plus 0, which is 4. So this is positive, this is positive. So whole thing is positive. So between negative 4 and positive 4, this expression is positive. Now what about a number which is to the right of 4? Let us suppose we have 5. Okay, so again in this, if I plug 5, so we have 4 minus 5, then 4 plus 5. 4 minus 5 is negative 1. 4 plus 5 is a positive number. Obviously, let's write it here also. So -1, we don't need to calculate it, just we need to find out the sign. So here it is negative, here it is positive, so overall we will get negative, but we have this restriction. Now then domain will be, our domain of the function will be only this very partition from -4 to +4. Okay, so domain will be now let us see whether we have to include -4 or +4. Yes, we need to include -4 and +4 because our expression will be greater or equal to 0 if we plug here -4 or +4. Even if it is 0, we don't have problem. So our domain will be from -4 to +4. That is why we are taking this square brackets here. That means -4 and +4 are included here, and all the numbers between them. Now let's take another question. Let us suppose we have, let us suppose f of x is equal to, let's take a number. Let's take an expression. Let us suppose x square minus 9 this time. Now again, this is in the numerator. What should happen? We should, for this to be defined, x square minus 9, it should be greater or equal to 0. Okay, that means we can write it like this: x square, in place of 9 we can write 3 square, it should be greater or equal to 0. Or we get x minus 3, x plus 3, it should be greater or equal to 0. Now again we need to do the partitioning of the interval. So from -infinity to +infinity, let us take two numbers. We have -3 and +3. So let us suppose we have -3 here, +3 is here. Okay, how we are taking this? So we put x minus 3 is equal to 0, then we take x is equal to 3, then we plug it here. Likewise here x plus 3 is equal to 0, or x is equal to -3, then we are plugging it here. Okay, so to partition the interval here. Having said that, since we want this expression to be positive, okay, let us take the numbers around the pointers on this. So to the left of -3, let us suppose we have -4. If we have -4, so we have x minus 3 times x plus 3. To the left, if we take -4, so we will get -4, -3, and here we will get -4 plus 3. So it will be -7, it will be -1. So we have negative into negative, which is positive. So to the left of -3, we have the positive value. Okay, so this will be the part of our domain. Now let us take from -3 to +3 any number. So -3 to +3, obviously we can take 0. So we have x minus 0 minus 3 times 0 plus 3. So we get -3 times +3. So we will get negative value here. Okay, that means this will not be the part of our domain. What about from to the right of the 3? Let us take 4. Okay, to the right of 3, let's take 4. So we have 4 minus 3, 4 plus 3. So 4 minus 3 is 1, it is 7. So this is positive, this is positive, positive times positive is positive, 10, 10, 10, 10. So this is also the part of our domain. So in this case, In this case, domain of the function, domain of this function f of x will be, so we have to take from negative infinity to this, so open interval negative infinity to -3. Inclusively we have to include it. Okay, then since neither negative, okay, so this is not the part of our domain from -3 to +3, then we have to take union from so then we have 3, so let me use the proper color, so we have 3 to positive infinity. Okay, this will be the domain of this very function. Now if we have this function in this form, that is, if we have this in the denominator, let us suppose it is like this, 1 divided by, so here also we have 1 divided by, if we have the rational function. So what will happen here? What will we do here? So here we should have the strict inequality. So since it is in the denominator now, so rule number 3 applies here. That means this should be strictly greater than 0, this should be strictly greater than 0, this should be also strictly greater than 0. Okay, that means in this case we don't need, or rather we don't need to include -4, so we will have open interval here and open interval here. You can check it by yourself. Likewise for this problem, since we have this expression now, this term in the denominator, again it should be now strictly positive, so positive, so positive. That means here this 3 will not be the part of domain, so we put open interval. Also this 3 will not be also the part of the interval, that is, this -3 will not be also the part of interval. You can check it by yourself also. So I hope I make myself clear in this video. So next we will find out the range of the function. If you how to calculate range of a function. If y is equal to f of x is a function, all the values of y for which x is defined is called the range of the function. Now let me explain it with an example. Let us suppose we have two sets, set A and set B. Set A contains elements, let us suppose -1, 1 and 2. Set B contains elements 1, 4 and let us suppose 12. Okay, and further let us suppose that 1 is related to 1, 1 is also related, sorry, -1 is related to 1, 1 is also related to 1, 2 is related to 4. Okay, this is set A, this is set B. Now what is the range of the function? Let us suppose f is a function which maps set A to set B, where set A and B are finite sets. Now range of this function will be all the values of y for which x is defined. So we set B, we can call it y is equal to f of x, or this is our output. Okay, different values of x's, or that here x means different values of set A here. Okay, so what we say, range of this function is all the values of y for which x is defined. Okay, now in this case we can say range of this function will be all the values of element B, or sorry, all the values of set B which have the pre-image in set A. 1 is the pre-image of 1, 1 is the pre-image of -1, 4 is the pre-image of 2, but 12 is not the pre-image of any element present in set A. So range will be here 1, 4, and 12 in fact will be the part of codomain. Okay, in case you are wondering what is meant by domain, codomain, I have explained that in detail in another video, and I have explained how to calculate the domain of different kinds of functions. You can check out that very video on this channel, and I will put it into the I button and also in the description. So codomain will be 1, 4, 12. Okay, now let me take another example to explain this definition. Let us suppose I have set A and we have set B. Okay, and let us suppose we have this time function f of x, y is equal to f of x is equal to 1 upon x. Okay, and in this case let us assume that set A and set B are infinite. That is, set A is the set of real numbers, set B is the set of real numbers. Now you tell me, can I get the output equal to 2? Or put it in simple thing, can I get output as 1 upon 2 for any value of input? So can I get y is equal to 1 upon 2? Yes, if x is equal to 2. If x is equal to 2, if x is equal to 2, y will be equal to 1 divided by x, which is 1 upon 2. So I will get output as 1 upon 2 if x is equal to 2. So here we have 2. So then x is in relation to 1 upon 2. Here I am saying 1 upon 2 is the pre-image of 2 also. Okay, so can I get, let us suppose 0 is output for any value of x? Now you can think about it. Okay, I can put x is equal to 0. Then y will be equal to 1 upon 0 because we have 1 upon x. But 1 upon 0 is not any number, it is undefined. Now 1 upon 2 is the part of the range. Why? Because it is the pre-image of 2. 0 will not be the part of range. Why? 0 has no pre-image in set A. Can I get 3? Okay, so can I get 3 as output? Yes, we can get 3. So if I plug x is equal to 1 upon 3, y will be equal to 1 divided by x is 1 upon 3. Transposing, we will get 3. Yes. If we have x is equal to 1 upon 3, y will be 3. Likewise for any value. Now in this case, what can I say about the range? Since A and B are the infinite sets, or we have this function y is equal to f of x. In this case, I can say the range of this function, okay, range of this function will be all the real numbers except 0. Okay, so for this function, range of this function will be all the real numbers except 0. If we plug any value except 0 in this equation, sorry, in this set, we will get a definite output here. Okay, now there are steps to calculate the range of a function, and let me explain those steps. Okay, we will take the simple questions first, then we will take the difficult ones. I cannot say difficulty is the subjective matter in this case. So let's suppose we have f of x is equal to x minus 2 divided by 4 minus x. Okay, so first step to calculate is put y is equal to f of x. Okay, so we put it equal to y is equal to f of x, means y is equal to x minus 2 divided by 4 minus x. Okay, or let's take a simple example first. Let us suppose f of x is equal to any, let us suppose x plus 1. Okay, so we put y is equal to f of x, so y is equal to x plus 1. Second step is express x in terms of y, so write this in terms of y, so we can write x is equal to y transpose y, here it becomes y minus 1. Okay, then third step tells us find the possible values for y. Now what will be the values of y here? So if I plug any value here for y, x will be defined. Okay, so if I plug 1, so 1 minus 1 is 0, so x will be 0. If I plug 2, 2 minus 1 will be 1, so x will be 1. 3, 3 minus 1, so x will be 2. So in this case, y will belong to set of real numbers. Okay, so the range of this function, so I can say the range of the given function, range of f of x will be the set of all real numbers, and in interval notations we take negative infinity to infinity, and we put the open intervals because we cannot negative infinity or positive infinity, they are not the numbers, they in fact reflect the idea unboundedness. So we cannot use the square bracket. Square bracket is used to include a value in an interval. If I write 1 comma this 1 and 3 here in this fashion, so I am saying all the values between 1 and 3 including 1 and 3. So 1, let us suppose we have 2 and here we 3. By square brackets we mean this. If we have like this open interval, what we call this closed interval, and this open interval, and we have 3 here, that means between 1 and 3 all the numbers. So we don't include 1 and 3. Let us suppose we have only 2 here if this belongs to the set of natural numbers. So this square bracket includes the numbers in the interval, and that's why I am saying that we cannot put here infinity, okay, because then we have to count infinity as number, but infinity is not the number. Okay, having said that, we don't need to look at this. Okay, so range will be the all real numbers. Now what about step 4? I will be explaining step 4. It's very crucial for some functions, in fact for scaled functions. Eliminate values by looking at the definition of the initial function, and I will be explaining this also. Now let's take this example again. So y, first we put y is equal to f of x, then express x in terms of y. Okay, so cross multiply then, so we get 4y minus xy is equal to x minus 2, or we can write transpose this here and this here, so we get 4y plus 2 is equal to x plus xy, or let's take x common, so 4y plus 2 is equal to x1 plus y, or x will be equal to 4y plus 2 divided by 1 plus y. Okay, so we have expressed x in terms of y. Now we need to find out the possible values of y. Now here if I plug, if y is equal to -1, so the denominator will be 0. Okay, if y is equal to, we know that denominator cannot be 0, that means 1 plus y cannot be equal to 0, that means y should not be equal to -1. If denominator is 0, so it is undefined here. So what will be range? So we can say y belongs to the set of real numbers except -1. That will be the range of this very function. Okay, now let us see what we have done. This was step 1. Okay, and this was step 3. We have to that is find all possible values of y. So y belongs to, we take all real numbers except -1. That will be the range of this very function. Now let us explain step 4 with an example. Okay, for that let us take a question and be very careful. Let us suppose we have a function f of x is equal to, let us suppose we have 1 divided by under root x minus 2. Okay, so first step is put y is equal to f of x. So y will be equal to, f of x is 1 divided by under root x minus 2. Now what will we do then? Let us square both sides. Let us put square here, and if I put square here, so we will get square for this thing. Okay, square and root gets cancelled, or y square is equal to 1 divided by x minus 2. Okay, Let us do cross multiplication. So we'll get xy square minus 2y square is equal to 1. So we have to express x in terms of y. So we can write x y square is equal to 1 plus 2y square, or x will be equal to 1 plus 2y square divided by y square. Okay, this was step 2. We have expressed x in terms of y. Now we are being told to find possible values of y. Okay, we know here that y cannot be equal to 0. Okay, if y is equal to 0, then this term upon 0, so division by 0 is not allowed. So we can safely say y cannot be equal to 0. Okay, if y cannot be equal to 0, in this case, so can I say range of this function is all the real numbers except 0. Okay, I am saying range of this function is all the real numbers except 0. But here is the twist. Why? Since we have a square root function here, we have the square root function, and we know that square root, now this comes the fourth step, eliminate values by looking at the definition of the initial function. Since our function is y is equal to 1 divided by under root x minus 2, and we have explained it in earlier video also that this term should always be strictly greater than 0 if the under root is in the denominator. So square root, if I have simple x minus 2, so it should be greater or equal to 0. Okay, because we cannot take the negative values, because negative, if I get here negative 3, so it will be an imaginary number here. Okay, so it is not possible to in the real number system to include square of a negative number, rather under root of a negative number. That's why we put the restriction that this should be greater or equal to 0. But if it is in the denominator, two conditions should be met. First, we know the denominator should not be equal to 0. Okay, if this is in the denominator. Second is this expression should be greater or equal to 0. When we combine these two, that means it should be strictly greater than 0. Okay, that means if I say range of this function is all real numbers except 0, but this condition is violated here, that means we can only take positive values here for this y to be positive. So in this case I can say range of the given function will be, so range of the function will be all the, or if I put it like this, infinity. So we take only, if I have the number line negative infinity, if it is 0. Okay, so range of this function, initially we know that y cannot be equal to 0, so y is not the part of this interval, so that's why we have taken open interval. And since we have the square root function, that means we should only get the positive values, although we got y belongs to all real numbers except 0. But when we look at the fourth step, we have to eliminate values by looking at the definition of the initial function, because in the initial function we cannot take the negative values. That is why we have to eliminate from this range those very values, so we take only positive values. So range of this function will be in fact from 0 to infinity, and we take open intervals here because 0 is not the part of range. Okay, let us take another example. Let us suppose let us say f of x is equal to under root, or let me rub this out why I am making myself. So let us suppose f of x is equal to, let us suppose we have a function under root of 9 minus x square. So first step is put y is equal to f of x, y is equal to under root 9 minus x square. Okay, since we have to write it in terms of x only, so we should get rid of this square. So this under root, let us square on both sides. Square and root gets cancelled. Y square will be equal to 9 minus x square, or we can write x square is equal to 9 minus y square. Okay, we know that here x square is always positive. Okay, we know that x square is always positive, because if we put any value here, let us suppose negative 2, and we square of any number is positive. So can we say here that since x square is positive, greater or equal to 0, that implies 9 minus y square, it should be also greater or equal to 0. Okay, if this is greater than 0, so this will be also greater than 0. Now can I write it like this? 3 square minus y square is greater or equal to 0. So this is a square minus b square, and it is equal to 3 minus y times 3 plus y. It should be greater or equal to 0. Okay, so how do we solve this inequality? For that, we put a number line here, negative infinity to infinity, and we set 3 minus y is equal to 0 and 3 plus y is equal to 0. That means if 3 minus y is equal to 0, it implies y is equal to 3. If 3 plus y is equal to 0, it means y is equal to negative 3. We call them the critical points. Now let us suppose negative 3 is here, positive 3 is here. Now let us see this interval. We have partitioned here it. Now let us take the numbers to the left of negative 3 and plug here. If I plug, let us suppose negative 4 here to the left of this. So if we have 3, then we have minus. We take y as negative 4, so we have minus this, then we have negative 4 times we have then 3, y is negative 4. So here minus into minus is plus. 3 minus 4 is negative number. So here we will get obviously minus into minus is plus, so 3 plus 4 is 7. So we'll get here 7. 3 minus 4 is negative 1. So we have positive, here we have negative. Our answer will be positive into negative, which is negative. So to the left of the interval we get negative values. We need this to be greater or equal to 0. Okay, positive, but between negative infinity to negative 3 we are getting negative values. Now let us see between negative 3 and 3. So let's take any number here. Let's take 0. Okay, so if I plug here 0, 3 minus 0 times 3 plus 0, so we will get this inequality. So between negative 3 and 3 we will get positive values. You can take 1, 2, whatever you like. Now let us see to the right of 3. So let us take 4. Okay, so we have 3 minus 4, we have 3 plus 4. So here we will get negative. 3 minus 1 is negative. Here we get positive. Again here we are getting negative. So can we say y belongs to y belongs to negative 3 to 3, positive 3. Why I am taking the closed interval? Because negative 3 and positive is included here, because at negative 3 and positive 3 we got it equal to 0. Having said that, so this was step 3, find possible values for y. Now step 4 is important. Eliminate values by looking at the definition of the initial function. What was our initial function? F of x is equal to, that is y is equal to under root 9 minus x square. Okay, now we know that this square root function can take only positive values. That means it should be greater or equal to 0. And here we are getting y from -3 to 3. That means from this interval we cannot get negative value. That means we have to remove the negative values from the interval. So let us take 0 here. Okay, so we have to eliminate those values which make us this expression negative. Okay, so let us suppose it is here 0. So our range of the function will be from 0 to 3. So we will have 0. So how do I write it here? So we have 0. We have to include 3. Okay, this is from the fourth step. Because we got y, the possible values of y from -3 to 3, but since we have the square root function, it is always greater or equal to 0. Okay, we cannot get a negative number here. If we cannot get negative number, then we have to remove the negative values from this. Then a range of the function will be from 0 to 3 here. Okay, so let's take another example. So let me take another example. Let us suppose f of x is equal to this time x square minus 4. Okay, y is equal to x square minus 4. Okay, x plus x in terms of y, so squaring both sides, this gets cancelled. So y square is equal to x square minus 4, or x square is equal to y square plus 4. Okay, now we know that here square of any number is positive. That is, x square is positive. That means y square plus 4 should be also positive. Okay, now what will be the range here? What will be the possible values for y? We know that this is positive always. This is always positive. That means y can take any real value. Okay, but this is find possible values of y. So y belongs to real numbers, or like this, minus infinity to infinity. But we have to see fourth step, eliminate the values by looking at the definition of the initial function. But our initial function was a square root function, x square minus 4, and we know that this should be greater or equal to 0. Okay, if it is in denominator, obviously it is in the denominator here. So then what we need to do, we need to eliminate the negative values from this interval. That means range of, or let me write it magenta's, range of f, this function will be from 0 to infinity, including 0. Okay, 0 will be obviously the part of the range here. Okay, so let's take another example. Let us suppose this time we have a function. Let us take okay, so let me take a function f of x is equal to 1 divided by 4 minus x square. Okay, again write y is equal to f of x 1 divided by under root 4 minus x square. To get it in terms of x, let us take square on both sides. That means y square will be equal to, square and root gets cancelled, we are left with 4 minus x square. Cross multiply now, so 4y square minus x square, y square is equal to 1, or x square y square is equal to 4y square plus 1, or x square will be equal to 4y square plus 1 divided by y square. Okay, we have expressed x in terms of y. Now we know that square of any number is positive. That means our x is greater or equal to 0. Okay, if x is greater or equal to 0, then 4y square plus 1 divided by y square should be greater or equal to 0. Okay, we also know that y square we cannot have the denominator as 0. That means y cannot be equal to 0. Y cannot be equal to 0. Then it would be undefined. This thing we know here. Okay. And we also know that y square is always positive. Okay. So here we have positive. Then this should be also positive. Our numerator to be positive. Either we should get this negative. If numerator is negative, denominator is negative, then we will get positive. If numerator is positive, denominator is positive, then again we can get positive. But if one of them is negative, then we will get negative. But our expression is, so our condition is we should get positive here. So here we have seen y cannot be equal to 0, but y square is always positive here. That means our numerator should be positive for this expression to be positive. So for that means our 4y square plus 1, 4y square plus 1 should be positive, obviously. Four y square plus 1. So how do we write it? So can we write it like this? 2y square plus 1. Sorry, it is here negative. Here it is negative. Here it is negative, because here I have done miscalculation. Okay. So this whole should be greater than 0. Greater or equal to 0. So this is a square minus b square. So it is equal to 2y minus 1 a minus b times a plus b. It should be greater or equal to 0. Okay, again let us form the line from negative infinity to positive infinity. Now for this to be 0, let's take the critical point. So we equate this term to 0, that is 2y minus 1 is equal to 0, or 2y is equal to 1, or y is equal to 1 upon 2. Likewise, if we plug 2y plus 1 is equal to 0, we will get 2y is equal to negative 1, or y will be negative 1 upon 2. So let us put negative 1 upon 2 here, positive 1 upon 2 here, and let us see what will be the possible values for y here. Now to the left of negative 1 upon 2, what number we will get? We can get negative 1. Okay, so we have 2y minus 1, or we have 2y plus 1, and our condition is it should be greater or equal to 0. Let us plug here negative 1. So we will get 2 into minus 1, 2 into negative 1, then minus 1. Here we will get 2 into negative 1 plus 1. So here we will get negative 2, negative 1. Here we will get negative 2 plus 1. That means here we will get negative, and here also negative. Negative times negative is positive. So to the left of negative 1 upon 2, we got positive values for y. Okay. Now to the right of negative 1 upon 2. So between negative 1 upon 2 and 1 upon 2, obviously 0 lies. So let us put 0. You can pick any number between minus 1 upon 2 and 1 upon 2. Let us plug 0 here. So it will be 0 minus 1. Here it will be 2 into 0 is 0 plus 1. So negative 1 times positive 1, we will get negative. So between negative 1 and between negative half and positive half, we get negative value. Let us show it with the red color. Okay, so let us see to the right of 1 upon 2. Let us take any value. Let us take 1. So 2 into 1 is 1 minus 1. Here we will get 1 minus 1 is 0, and 2 plus, sorry, so 2 plus 1, which is 3, so we get 0. Okay, so to the right of negative 1 upon 2 we are getting, sorry, to the right of 1 upon 2 we are getting positive values. To the left of negative 1 upon 2 we are getting positive values. Okay, so y belongs to, so y belongs to, we have negative infinity to negative 1 upon 2 union, because 1 upon 2, negative 1 upon 2 is included here. Then from 1 upon 2 to infinity. Okay, find possible values. These are the possible values of y. Now we need to eliminate the values by looking at the original function, the definition of the initial function, which is our original function. Where is our original function? This is our original function. We know that y is equal to 1 divided by under root 4 minus x square. And we, as I have explained earlier, since we have the square root function and we have the square root in the denominator, that means it should be positive and it should be strictly positive here. Okay, so y should be strictly positive because it is in the denominator, it cannot be equal to 0, and since we have the square root function, it should be positive, greater or equal to 0. Okay, when we combine these two we will get strict inequality or strictly greater than 0. That means our range of the function is, we need to eliminate the negative values here. Okay, so from this we need to eliminate the negative values here, so we can take it from 0 to infinity. That means range will be from 0 to infinity. Okay, so possible values are these, but since we have the under root function, we need to eliminate the negative values here so that this y is positive. Okay, now we can think of another different kinds of functions. Okay, so you can also solve a function and give me the answer in the comment section. Let us suppose f of x is equal to 1 divided by under root, let us take 25 minus x square. So give me the range of this very function in the comment section. I will be waiting for your answer here.